சார். ராஜா சார். குட் ஆஃப்டர்நூன் சார். சார் கேக்குதுங்களா?
Good afternoon, Balaji.
சார்
Yes.
2 மினிட்ஸ் சார். இப்பதான் செஷன் முடிஞ்சிருச்சு. 11:00 11:10 எல்லாம் வெளிய போனாங்க. 2 மினிட்ஸ் ஜாயின் பண்ணிடுவாங்க சார்.
No, we'll start at 11:30. That is
ஓகே
not
சார். ஃபைன் சார். ஓகே சார். 11:30 ஸ்டார்ட் பண்ணலாம் சார். நீங்க கூட ஜாயின் பண்ணிடுங்க சார். தேங்க் யூ சார்.
okay.
Indujo, I think we can start.
A very good morning and welcome to the second day and the fourth session of the online faculty development program on data analysis using econometric models. This session will be on a preliminary understanding of time series model. I would like to welcome our speaker, Professor S. Rajasedudure, sir. He's a professor at the School of Economics, University of Hyderabad. He has worked as an assistant professor in the Department of Economics, Pondicherry University from 2010 to 2017, and as a lecturer at the Madras School of Economics prior to that. He has a PhD from Madras School of Economics and a master's degree from Anna University, Chennai. He has published numerous papers on macroeconomics, applied econometrics, and financial economics. Now, I would like to invite Professor Sedure, sir, to the platform.
Good morning, all of you.
Good morning, sir.
My audible?
Yes, sir. You're loud and clear, sir.
Okay, fine. So I'll thank you for the nice introduction. I'll be more happy to share my knowledge here. So what I do is I'll stop my video so that it won't affect our browsing speed. So if you have, I hope this is a mix of both research students as well as faculty. But anyhow, what I do is I'll start with the basic this time series and what are all the various method we have, and then slowly you can do some higher level of analysis and understanding. Okay, so if you have any questions in between, you can stop me anytime and ask me. And also I prefer to have interactive class. So it's fine for you to ask any question in between. And otherwise also you can type your questions in the chat box, or at the end of the session also we will have some time for discussion. Okay.
Yes, sir. Clear, sir.
Right. So I'll share my screen.
Sir, please, sir.
Can you see my screen?
Yes, sir.
So can you see my PowerPoint?
Yes, sir. The screen is visible.
Okay, so what I'll do is that I'm going to go through this presentation for some time, and then I'll switch to some examples, which will be mostly in Excel. I hope all of you are familiar with Excel. And then, switch back to the presentation and then explain the things. Okay, so it will be a mix of PPT as well as the Excel. Okay. So now to start with, time series econometrics. In time series, there are all of you aware that there are three types of data. Okay, so one is cross-section data, the other one is time series, the third one is panel or pooled data. So the point we have to keep in mind is that econometrics used for these different types of data is different, and econometrics used for different scale of measurements of variable is also different. Okay, so we can't blindly apply the econometric techniques for whatever data we have. Okay, so that that is not going to work here. So every type of data has its own methods and techniques. So we have to first understand the types of data, the characteristics of this data, and then we have to identify the techniques which can be applied here. So why I'm saying this is that, we might be using ordinary least square methods, which is actually developed for cross-section data. It cannot be blindly used for every type of data. So that is the point we have to keep in mind before starting this. Okay, so time series is, first we will start with the basic definition. See, cross-section is, so cross-section, all of you know that, when you collect data where there is no time in it. Okay, so if you collect data of all of your heights, so if you have a class of 100, and if I collect the heights of each and every one of you at this time point, then it becomes a cross-section data where time is not there. If I am collecting your heights over a time, okay, then it becomes a panel kind of thing. But time series is something which is a sequence of measurement over time. Have to two things we have to keep in mind here. One is it is sequence of measurement of a particular variable, you can say, over time. But usually it should be obtained equally spaced interval, monthly, quarterly, yearly. So that time should be equally spaced. You can't mix up these things. So you can't have monthly data and then quarterly data together and try to do some analysis. That is not possible. Okay. So and any analysis for a time series data, it should be for a particular time, equally spaced intervals for a particular type of data we collect. So we have daily, monthly, quarterly, yearly, and also we now have data collected on less than daily basis. Minute by minute data is there, second by second data is there. If you go and collect data on stock market, so we have minute by minute data, second by second data, and all those things. So all the data which are collected with the frequency less than daily and less than daily, we call it as high frequency data. So above that, monthly, quarterly, and yearly. We also have weekly data. Okay. This daily and less than daily data are called high frequency data. Again, we have to keep in a point here that for high frequency data, the econometrics is slightly different. And for the rest of the other frequency data, the econometrics is slightly different. Okay, so we can't use the methods developed here for monthly, quarterly, yearly frequency data, which we call it as low frequency data, can't be applied directly to high frequency data because the characteristics of each of these data is different. So that is the main point we have to keep in mind. Okay. So a data set containing observation on a single phenomenon observed over multiple time periods is here. The important thing is that both the values and the ordering of the data points have meaning. Data, the values as well as the order. 1994 should come after 93 and before 95. If you change the order, then it is not a time series data. So here, but in cross-section data, it doesn't matter. Okay. In cross-section data, ordering is not a a big deal because if you collect data on heights of the class, you can arrange it in any order and do the analysis. Your results are not going to change. But if you change the order in a time series data, then obviously it has its own complexities. It has its own problems. So here, the values as well as the ordering of the data points have meaning. Okay. Now, there are two things here. One is, so time series data is data collected on a particular variable or the period of time. Okay, fine. Now, there are two ways of looking at it. One is way of looking at the time series data, and we call it as classical time series models. And there is another modern view of time series models. Okay, so there are two things. Ultimately, the focus or the purpose of any time series modeling is to do a forecast. Okay, so the main idea of having a time series analysis is doing a forecast. But both these classical as well as the modern view of time series techniques are focused on that, but there is a difference in their total understanding of the time series. So first we'll see the classical view, and then I'll introduce you to the modern view of how time series is looked at. Okay. So in the classical view, the time series. See, time series, for an example, you take inflation collected or the exports of the country every month. So all these are time series examples for time series data. What are all the components of this time series data? See, if Y is the data, if Y is, for example, is the exports of the country for months, monthly data collected for some 10 years. So the components are mainly, this is actually the classical view. Components are mainly the trend component, cyclical component, seasonal component, and irregular component. Okay, so there are two ways we can compose. One is multiplicative way of decomposition, and the other one is additive decomposition. Okay. In the multiplicative, see, all these things are in all these components in a minute. But you have to keep in mind that there are two ways to construct the same variable. Okay, so one is multiplicative and the other one is additive. Both will be, giving almost a similar kind of results and decomposition, but one is, say here it is called the seasonal index, and here it is called the seasonal component. Here it has been benchmarked as an index. Here it is benchmarked as a component, which means the value itself. So, so what I'll do here is I'll explain these components, and then somebody is saying that there is a voice break. All of you can hear me?
Yes, sir. It's clear, sir. Maybe it's their issue, sir.
Okay.
Sir,
Okay, fine. So I'll go with this additive thing because it makes understanding much easier. Okay. Okay, so the first one is T, which is actually the trend component. we have two types of trend. I'll explain it to you, which is a linear and non-linear trend. The second component is seasonal variation. The patterns of change within a year typically repeating themselves. Okay, so seasonality is an important aspect in time series analysis. So that happens only if you have a data which is less than a year frequency data. So mostly, monthly data or quarterly data, we will have this seasonal effect. So the seasonal effect is nothing but, if you take exports or if you take sales of any particular commodity, or you take the demand for travel, so the demand for train tickets will be more when there is a vacation. Okay, so during the month of May and June, there will be a huge rush for the train ticket sales. And even for any other sales of any commodity, if there is a festivities, uh, and during that period of festivities, then there will be a huge increase in the sales. So these seasonal effects, which happens within a year, but it happens regularly for every year, during the month of May and June for travel, and during the month of November and December for festivals, like that, then we call it as seasonal variation. Okay, so patterns of change within a year, but typically, happening every year. So that we call it as seasonal variation. And we also have a cyclical variation, which is actually, rise and fall over a period longer than a year. So here, the difference between seasonal and cyclical is that, cyclical happens every 5 years or 10 years. Say, for example, if there is a flood in Chennai. So last time it happened is in 2015. So then, after all this time, it happened the last season. So every 6 years or every 10 years, if something happens, which is greater than a year period, then we call that as a cyclical variation. Okay. And the last point or the component is called the irregular component, which is an error component, which which is beyond the control of anybody of us. There are some errors which might happen due to a lot of things. Okay, so that part will be termed as this. So in the classical way of looking at time series is that any time series data can be decomposed in these three major heads: trend, seasonal, and cyclical. Okay, and the irregular component, it will be always there. Some level of errors will be there all the time, so which is beyond our control or understanding. So what they thought is that, if this is the components which constitute the time series, then we can individually first decompose any time series into these three components, individually forecast these three components, and then recompose it to get the forecast of the value of the variable. Okay, so that's the basic idea of doing a forecast using this classical decomposition method. Okay. So there are some steps involved in this. One is treat extreme values or irregular for any time series analysis. The first best thing we have to do is we have to make a graph. Okay, but not only for time series econometrics, just for any econometric analysis with the data, make a graph up, because the graph itself will tell us a lot of things. So you can understand how it is, what's the pattern of it, and whether there are any extreme values is there or irregularities are there. See, if one extreme value which is entered into the data because of human error, if you type the data, if you wrongly typed and put 1 0 extra, then obviously we'll have a totally different data set. So we have to first see that whether the data is clean and without any errors. And also, we can observe a lot of things by making it as a visual plot. So the first thing is, after making a graph of any time series, we have to see whether there is any extreme values or irregularities in the data. There are extreme values, then we have to treat it. So what do you mean by treating extreme values? It is to see why that extreme value happens. Okay, so if it is due to a human error, then we can correct it. But if there is an extreme value due to some other reasons, say for example, if in a sales of a particular commodity, if on a particular month, if every sales representatives or salesmen are going on a strike, then obviously there will be a huge fall in the sales. Okay, so that might be a one-time event which is not happening every year. If it happens every year, then it is not a extreme value or a irregular thing. If it happens only at a particular year, there is a fall because of some problem. See, you can take, if you take last 2 years of data of any sales data, you might see a very big drop in the sales during the lockdown period. Okay, so these things we should treat, because if you want to have a better forecast if you want to understand the better pattern of the time series data, then we have to treat this, because these are all extreme events, one-time event. Because of that, there is a drop or there will be a rise also. So in that case, we have to treat these values. So how to treat, that if there is a one-time fall in the sales, then in a particular month, then you can take an average of the previous month and the average and the next month, and then keep that average as the value rather than the actual drop in that sales as a value. So there are different ways to treat these extreme values, but that depend upon the reason for the extreme value. Okay, so that should be the thing. So the next thing is that once we know that the data what we have is clean, we have to fit a trend line. Then we have to construct a seasonal. A trend line and constructing a seasonal component, there are some methods to you with an example, so that you can easily understand these things. So after constructing the seasonal component, we can construct the cyclical component also. So once that is done, we have trend, we have seasonal, we have cyclical, then we have to forecast. The error component can't be, modeled. Anything which can't be modeled can be called as error in econometrics. Okay. So that part will be there. And also you have to keep in mind another thing in forecasting, there is nothing like will give perfect forecast. The better model can be identified by the one which gives an closer forecast. There will always be a mean square error, or mean absolute error. Obviously, we have to choose the model which gives us the lesser mean square error or lesser mean absolute error. Okay, so there will always be an error part in that in forecasting as well. So we have to live with that error thing. Okay, any questions as of now?
So generally, we ask participants to ask the questions in the end of the session, sir.
Okay, fine. Okay, so now I'll move on to the example. And so here what I have done is I have taken this additive decomposition method where we have trained the seasonal, cyclical, and irregular component as a so here, instead of taking data, what I am trying to do here is that I'll create a data. Okay, so that, see, one of the best way to understand the goodness of any model is that, you create a data which we call as simulation in econometrics. So here, we can create data and then see whether our model identifies whatever been created. Then, then we can be of very sure that it will work better for our actual data as well. Okay. So here, since we are creating the data, we know the actual inputs going into that time series, so that we can see what I'm trying to do here is that I'm actually creating a trend component, seasonal component, and irregular component. Okay. And then I'm adding everything to get a time series. Okay. Why? And then I'll implement a method to that time series and see whether that decomposes these trend, seasonal, cyclical components. Okay. If it can decomposes closely these components, the method, then we can say that the method can be applied to any other time series decomposition. Okay, so it is a kind of validation of the model if we do something like this first. Okay, so what I'm doing here is that I'll create a trend component, which is I'm creating it as 5 plus 0.7 times t. T is the time period. Okay, so if see if I take a 50 time period, then I'll have t1 from 1 to 50. And the seasonal component I'm creating like this, where we actually give creating a seasonal component as a sine curve. Okay, since seasonality happens within a year, and then the same pattern should be coming every time. Okay, so this function, sine function actually fits into that case well. So we are going to use sine for that. So here again, t is the same time period, and this is pi and divided by 6. So if I give 6 here, then the pattern, cyclical pattern, seasonal pattern can happen every 6 months. If I give 12 here, then it happens every year. But as we theoretically know that seasonality happens within a year, so I'm giving it as 6. So, and then you can also create a cyclical pattern similar to this with rather than giving 6, if you give 60, then you are actually creating a cycle which occurs every 5 years. Okay, but I'm not going to do that. So I'll stop only with this, because this seasonal and cyclical has the same kind of thing, but only the which is happening within a year and something is happening over the year. So I'm not going to repeat the same thing for the example. But I'm going to do the irregular component, which actually is an random error. So I'm generating the irregular component as this, which is actually coming from the random. The irregular part we assume is in the econometrics also we assume that the mean of the error should be 0. Okay. So I am creating an irregular component, which is actually nothing but the random thing where the mean of the irregular component adds up to 0. So now what I do, I'll go back to Excel and show how to create these series. Then we will come back to the analysis part, how to fit a trend line, how to do the seasonal component and all those things. So can you see my Excel?
Yes, sir.
Yes, sir.
Okay. So what I have done is the same thing. So the first column, which gives me the time, the T. Okay. The time. So I have taken some 50 time period. So we have to, think that it is monthly data because, seasonality happens only for less than year frequency data. So the trend I'm creating, so I have started like this, 5 plus 0.7 T. So the T here is the time. I'm taking it like that. This period, the trend. Make a graph of this, then you will get a exactly straight line here. Seasonal component, as I told you, we are creating it as a sine curve multiplied by sine of. So there is a function called sine in Excel. So you can use that. Sine of t, again, this is t, which is the time divided by, again, pi is a constant. You can give the value of that pi, or there is a function in Excel, pi, open bracket and close bracket, that will give you the value of pi divided by 6. So if you change this 6 into 3, then you will get a different sine curve where something happens every 3 months. If it is 6, then you will have something different. Okay, so this number actually determines the type of. This is irregular component. I start with constant 2. Anything you can start initial value. This is again the same as what we have seen here, 0.4 multiplied by the past value of plus an error. Okay, so here to create a random error, what I am going to do is that there is a function in the Excel which actually gives us some points from the standard normal distribution. Okay, so all of you, I hope all of you know there is a standard normal distribution where the mean is 0 and the variance is 1. So if I randomly pick some values from that distribution, that becomes my random error. Okay, so how to pick randomly some value from the standard normal distribution? So there is a function which actually gives you the standard normal distribution. This is the function for that, as norm S inverse. And then to pick randomly some number, we have a function called random open bracket. Okay, so say for example, if I type it, this will give me a number which ranges from 0 to 1. Okay, so here it has come 0.46. Okay, the value corresponding to this probability will be picked here as random number in the distribution. Okay, so that is what we are going to do. See, for every click, there will be a different value coming here. It is totally random. We are not doing anything. The computer itself picks the value. So I'm going to use that here to get a random error. Okay. So this is same everywhere. So what happens here is that even though it takes the lagged value of this thing, which is D3, 0.4 times this, plus a random error, that actually becomes a, if I take the average of this, so most probably, I'll be getting somewhere close to 0. If it is not coming, see, if you are taking a huge number of observation here, like 500,000, then will automatically get these values. But this is actually for every time period you'll get every click you will get a different value. Okay, so here it is, average is 0.19. If I do another time, then this becomes okay. So the point here is that if you increase the number of observation, then obviously you will get this. Now, so we have trend, seasonal. If you want, you can also create a cyclical component by giving the same sine curve with higher frequency, so that the cycle years or every 10 years, because we have only 50 data point here. I'm not going to use which actually if you consider this as a monthly data, it is almost 4 years of data. So that's why I'm not including the cyclical component. If you want to examine this for a bigger data set, you can do that. Okay. So what I do here is that I'm simply adding all this as my y, and also I'm including another error component here. If you want, you can do that. Otherwise, also you can because we already add a error coming in the regular component. If you want, you can need. So this is the time series which we have created by creating a trend, seasonal and irregular components and then summing it up. If I make a graph of it, then my graph will look like this. Okay, so you can see that there will be a peak happening every year, right? So there is a seasonal pattern, and then there is also a trend, and there are some irregularity in this. Okay, so now we have to see, this is the series which we have created. Now we have to go back to the technique, how to identify. See, now in the real world, what happens is that we don't have any information of this. Okay, we have only information on this. So now using this, we have to get these things. Okay, so that is what we call it as decomposition. So how to do that? First one is we have to estimate the trend. There are two types of trend here, but what we have seen in the created data is a linear trend. Linear trend means that the increase is by constant amount. Because we have the slope coefficient, if the slope coefficient of the straight line remains a constant, then then we have a linear trend. If it is not a constant, if it is increasing by an increasing amount or decreases by a decreasing amount, then we call it as a non-linear trend. Okay, so both these trends can be estimated from a linear regression model. So I'll show you how to do that, but we have to keep this in mind. And also, if you graph the variable, you should see that whether there is a linear trend or non-linear trend. Accordingly, we can estimate the trend. The second thing is to identify the seasonal component. The first thing we have to do here is compute a 12-month centered moving average. See, all the seasonal component or seasonal index are calculated using this moving average thing. So what is the moving average? So if you have data like this, this is the time period, and we have data of y1 to y4. Moving average is nothing but the average of all data points, but it is centered, so you have to keep the average at the center point. So that above and below there will be 6. Moving average is something we have to keep the resultant moving average at the center, so that we are taking the average of the previous values and the after values. You can also have different types of moving average. You can simply take the moving average only with the previous values. Okay, but again, every moving average will give you a slightly different seasonal component. This is where there is some level of art coming in. We can't simply say that econometrics is a science, because most of the time what we do is that a lot of techniques here we have to use a trial and error basis to find out a better model. Okay, so different moving average will give you a different seasonal component, but see, and also the seasonality is every 3 months. If you see a peak in the data, we have to do a different moving average method. Okay, but what you have to keep in mind is that moving average is the way we construct this seasonal component. There are different ways we can construct the moving average. Every moving average will give you a slightly different seasonal index, but doesn't matter. At the end of the thing, what we require is that forecast. So if you have a forecast which mean absolute error or mean square error is very small, you can be happy with the moving average method which you have used. If there is a wide difference, then you can always come back and try a different moving average method to construct the seasonal component. Okay, so now once this moving average method is calculated, then you have to take the difference between the actual data, which is this, and the moving average, which is this. That will give you the seasonal component. So once we have the seasonal component, if you see here, so this is for the 7th period. If it is considered as a month, then this will be the 7th month, July of the year. Okay, so this if you have 50 data points, then we have almost 4 years. So there will be 7 July coming. Sorry, for July is appearing in this data point. Right? So this July and the 14th point here will also be not 14th point. 19th point will also be in another July, like that. So what we have to do is that we have for July month, we have to take an average of this seasonal component. So that is what we are mentioning it. So average it for each season. And then, see the average seasonal component should add up to 0. But if it is not adding up to 0, then we have to normalize it. I'll explain this while I'm showing you the example. Okay. So once we normalize it, then we are done with the seasonal component. So that is actually the seasonal component for the time period 1 to 12. That can be used, for every year. So you will have 12, if it is a monthly data, you will have 12 seasonal components that can be used for every year. Yeah. For the forecast also, we are going to use the same seasonal component. If you want to consider the cyclical component, the same thing you can do it to construct the cyclical component as well. Okay, but in our case, we are not using that. So what you can do is that in the cyclical component, it is, so once your trend and seasonal components are ready, then you can have the cyclical plus irregular component like this. Okay, so the remaining part will be the cyclical regular component. And if you feel that there is some cyclicality in the data, then you can also do the same averaging for different time period and take that as a cyclical component. Otherwise, if you see that there is no cyclicality in the data, then you can consider the remaining portion as the error thing. So which obviously if there is no cyclicality, the irregular component, even though we have created it in the example, but it adds up to 0. So anyhow it will be there. That can't be modeled as such. So we are going to keep it as such. Okay, so once we have this, then we can do the forecasting. So once you construct the trend, seasonal component, then we can do the forecasting. Okay, so what I do now is I'll go back to the example and tell you how to do these two things. Okay, so once that is done, then we will move on to the modern view of time series analysis. Oh, the trend, we have the it here. This half of this. So this is the y. Okay, so this is nothing but the y. Okay, so the first step is to see whether any extreme values are there or any irregularities are there. So there is no extreme value. See, say for example, if for this particular data point, instead of this value 25, if you would have wrongly entered 250, then you'll have an extreme value somewhere here. So if that is the case, then you have to treat that. Otherwise, if the data is clean, then we can forget about these things. So there are two things you can do to find out the trend. One is if in Excel, there are multiple ways you can fit a linear regression model. So the simplest way is, you make a graph. Here I am making a graph of y, and the x value I am giving it as the time period. This is y. Okay. And the x value is the time period, and y axis will have the y value. You select the data points and right click. So you will get an option to add a trend line. Okay, so if you add this trend line, so you have to fit a linear trend line, and then you have to say that display equation on the chart. Okay, so once you give this, so you will have a trend line, and also you will have the equation on the chart. So this will be the alpha parameter, intercept of the line. This will be the slope coefficient of the line. Okay. So instead of doing this, you can use these values to construct the trend. Okay. So if you want to use, then you can use the values to construct that. See, what I have done here is that I have made it more dynamic. Okay, because there is some randomness into the see, this is fixed, this is fixed, there is no random value is coming, but the irregular component has some random value. Okay, random error is there. That's why for every click, Excel will give a different value. Okay, if you see here also, for every click, or if you press the button F9 in your system, then every press of F9, you will see that the data is changing. Once the data is changing, your intercept and slope coefficient is also changing. If you see this, you can see it as well. Okay. So since there is some randomness in this, I have included the which is coming from these two creates this trend. Or what you can do is that if you want to create a trend, nothing but if you know that this is the intercept 7.30 0.6265 times the time is this, then you will get the so that you will get a trend estimation of all the, or alternatively, instead of doing estimate using the graph, you can also go to data analysis. Okay, there is a regression. So you select these values. Okay, the y values and the x values. So this is y value. Select the y value, and the x is nothing but the time. So you select that. Okay, so here if you see here, I have selected from here. If you are selecting from the first row itself, then we have to say that the first table name, confidence level, and you give any output range. And if I give it in a new worksheet, use these coefficients to construct back the trend line here. Okay. The trend line. So fitting a trend line is not a big deal in this particular thing. What is more or needed a little bit of thing is that we have to construct the seasonal index. So if you see, the seasonal index, you can see that the same pattern, the pattern appearing in first 12 months is going to remain same, because we have not given any randomness here. It is a simple deterministic seasonal pattern, so we are going to get the same values here. Okay, so this is the y value. What I am going to do is that I am going to take the 12-month centered moving average. So that is nothing but the average of this month. And the next thing will be the average of next 12 months and so on. Okay, so you can have an average up to this point, because after this point, you will be losing a value. There is no value here. So it will be only the 11-month moving average, not the 12 months. So we avoid this. So we'll stop our 12-month moving average with this. So once we create the 12-month moving average, centered moving average, we will take a difference between these two. For every click, there will be a change in the numbers, so don't worry about that. That is out of this randomness. Every time, the moving average will be calculated automatically. And then you can take the difference of this. So this difference is your seasonal component. So you will have seasonal component up to this point. And as I told you, we have to take an average, because this is July month. Again, we will have another July here. If I add 12 here, then 31 is also a July month. So we have to take an average of each of these July in every year. Okay. An average of these months. After taking the average of this, we have to take the average of the we have this average of seasonal components. It is not averaging to 0, so we have to normalize it. So how to normalize it? You just minus this part from this. So if you take since this is an average, if you remove this much from every seasonal component, then it should add up to 0. So the average should be adding up to 0. So once that is done, then we can use this as seasonal index. Okay. So since this starts from 7th month, we have to start from January. So what I have done here is that the January component is starting from this point, and this will be the February, May, June, and July will be this. Okay. So this is the seasonal component which we calculated from this method. Okay. Now we have to see whether these two are most close. Okay. So if you see that, this component, It's 8.33, 9.8, 7.9, and if you see here it is 0. Then you can see that the sign is also changing with values closer to this. So this particular simple, moving average based seasonal component is almost extracting the seasonal component out of this time series. Okay. So we have this. So once we have trend and seasonal component, irregular, we are not going to model it because we can't model the irregular part. So I'm going to add these two parts. Okay. So once you have this, if I want to do a forecast for this period, okay, so we have data from this to have the forecast. So the same seasonal component can be used here, and the trend can be estimated using the coefficients which we derive from the linear regression model, and then for the time period we have to use these values because up to 50 we have modeled. For forecast we are going to use these values, of this. Then we will get the trend forecast. We already constructed the seasonal component, so I'll get the forecast back. At these two will be my forecast. If you see the graph, so I have made the graph of forecast as well as the actuals here. See that even though there is some small deviations, but it almost captures the essence of the actual time series. Okay. So for, if you type F9, you will get a different data, but every time, the forecast is closely mapping the actual value, and the forecast will be like this. Okay. So it is on a similar line. Okay. So, any questions as of now? Because if there is any doubt here, I'll explain so that we'll move on to the next thing.
They are not asking questions. They ask only PPTs and Excel sheets.
Okay, that is great. Okay, fine. It makes our job easier, right? If no questions is asked, see, there are two interpretations of no questions asked. One is you fully understood. The other one is you understood nothing. Okay. So in both the cases, questions will not come. But anyhow, that's not a big issue for me. Okay, fine. So this is the classical decomposition and recomposition of time series data. After this classical thing, in 1960s, Box and Jenkins, two statisticians, come up with an idea that why you want to decompose and recompose all these things if 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 the data itself speaks for itself. Okay. If y is only a function of its own past values. Okay. Then if that is the case, because if you see the graph, you have a graph like what I have shown in the Excel sheet, then it is like, you have a y coming as a resultant of the past values of y. See, the basic idea they had is if time series can be imagined as a autoregressive process. Okay. Then, then the total interpretation and the total mathematics of behind that changes. Okay, so if you consider a time series, see, time series is nothing but tracing the time path of a particular variable. Okay, so if you have inflation as a variable, it starts from some point at time period t, and we are going to see how it travels through time. So what will be the possible next stop and next stop and so on like that. Okay, so if it has been modeled as a autoregressive process, then it boils down to a concept called difference equations in mathematics. So this is totally a modern view of looking the time series. Okay, so I'll give a small example for difference equations, and then I'll move on to the how we have to see the time series in this framework. Okay. Okay, so if you have an lumber company, which is wood cutting company, which owns 7,000 trees. Each year, the company plans to harvest 12% of its trees and plant 600 new ones. How many trees will the company have after 3 years? Okay. So they have 7,000 trees at the start of the time period. And every year they are planning to cut 12% of it. But they are going to plant 600 every year. Okay. So now, how many trees will the company have after 3 years? So we can, what you usually do. So 7,000 is the initial value. 12% of it will be cut. So plus 600 will be the addition. So the remaining thing will be the second time period trees and so on. So if we can write it in an equation, it will be like this. So the time period n, see if this is time period 1, if you take it as this, then this will be S0, which is an initial value. The initial value is nothing but the 7,000. And every time period, they are going to cut 12% of it. And then is n minus 1, n minus 1. So 1 minus 0.12 will be 0.88 plus. So this will be the equation. So this is called a difference equation because, be a function of the last value. And if I bring this here, then it becomes a Sn minus 0.88 times Sn minus 1. It becomes a difference.
Hello, sir.
Yeah.
Sir, can you please explain the equation once again? What Sn and Sn minus 1 that represents? I actually forgot writing down the question.
No, n is the time period. Say for example, we start with 0 time period. Okay, 0 time period we have 7,000 trees. Okay. Now n is nothing but t. In the previous example, I put a time period t, right? So here it has been represented as n, which is again representing the time period. So now if it is 1, which means that S0, what is the value, initial value?
7,000.
7,000, and we cut 12% of it. So 12% of it will be minus from the initial value, but
Plus
we
6.
all 600 to it. So this will be the function. Okay, this will be the equation. So 1 minus 0.22. See, this is again, the remaining thing. Okay, so once you cut 12% of it, 0.88% will be remaining there as trees. Okay, in addition to the 600 which are planted newly. Okay, so this will be the equation. So now, if I want, what will be the number 3 years after this? So for 3 years, I have to put 3 here. then this 3 minus 1 will be S2 plus 600. So for S2, again, I have to go back and calculate the S2, which will be 0.08 S1 plus 600. Again, for S1, I have to go back and calculate S1. So if if you have a difference equation like this, see there are two set of equations in calculus. This is difference equation because the time period is discrete, so we call it as difference equation. If the time period is continuous, then we call it as differential equations. Okay. Here, the thing is that what is the solution of this particular equation? Okay, solution in the sense that, if I want to know how many trees will remain there after 30 years, okay, so what I have to do, I have to calculate S1, S2 to S30 and then, compute. If this is the case, if this is the equation, then I have to compute for all 30 time period to get the value. But instead, if I have a solution which will be only a function of time, okay, and the initial value, okay, you have to keep this in mind. A solution to a difference equation. See, I'm making it as very simple because difference equation and differential equation itself is a big subject, and so you can't explain it in 10 minutes. But I'm trying to give the essence of it. So difference equation is something like this, where the time period is discrete. And why it is called difference equation? Because if I take this here, then it becomes a difference. Okay, you can call it as delta Sn. Okay, that's why it is called difference equation. A solution to a difference equation is something which will be a function only of the initial value as well as time period. If I get a solution of this difference equation, which will be a function of only the initial value, because the initial value we know, and all these parameters we know, and time period we want. Okay, so if I get a solution, if I plug in only these four values, if I get the numbers, I'll be more happy than substituting it for or calculating the values for every time period and deriving it. Okay, so the solution means here is only a function of the known parameters, initial value, and the time. Okay, for any difference equation, the solution means that. Okay, so if I want to calculate like this, we have to do it. So the first time period, there will be 6,760 trees will remain there. Okay, so I'm generalizing it, this function as this, Sn as
Sir,
0.8. Yeah.
sir, in the difference equation, sir, it will be a function of only time because initial value is constant for all the cases, no?
Yes, that's what I'm saying now. The solution should be a function of initial value because it's a constant which is already known. And then time. Okay, so if you have lag values, then you have to compute every time period. So a solution to a difference equation means known values and time. That's it.
Okay, sir.
So to do that, what we are trying to do here is that I'm converting this equation into I'm generalizing it. I'm putting A and B. So A and B can be any value. So once we have this equation, okay, so this is the solution to that equation. Okay, the derivation of the solution, I'm not going to explain it to you because you can go back and refer any standard you can get that. Okay, so if the A is 1, means what? The A is 1 means here in this, A is 1 means what? There is no cutting happening. That is not there. Only this is there. So no cutting happening. But we had 600 every year, every time period. So if A is 1, the solution will be the initial value plus n is time period times the P. So for 3 years, then it will be 3 into 600. 7,000 plus 1,800 will be 8,800 if no cutting is happening. A is not 1, then there is some cutting is happening. Can be greater than 1 also. So you can do that part. Instead of a proportion of the plants are planted, then it becomes greater than 1. See, here it is less than 1. So if it is not equal to 1, then this will be the solution. Okay. So A is the parameter, which is 0.88 in our case, and N is nothing but the time period, and SO is the initial value minus C. Okay. So this C part we call in difference equation as particular solution. So it can be derived like this. So B minus by A. Okay, so this will be the solution. So if you really want to get an answer for this, I'll show it in this. The initial value is 0. So is 7,000 and A is 0.88 and B is 600. So the particular solution C will be nothing but C B by 1 minus here. Solution is A power N, or if N is 3, then the solution will be A power N. Okay, so multiplied by this is 0 is this one minus C, okay, plus years you will have this many trees. 1 year 6760, which is exactly what we get here. Okay, so once we have a solution here, then there is no need for us to calculate every step. If I want for 30 years, this will be the number of trees available there. So the solution to a difference equation will be like this. Okay. The same idea has been, carried in time. Here, a variable y is considered as an autoregressive function. Okay, so it's a function of its own past values. Okay, so if something like this is there, if time series data yt is own past values like this, then this is also kind of difference equation. So it has two different solution. Okay, so since we have a constant here, as like the previous example, we have two different solution to this. One is the C, which is the particular solution, and the other one is the homogeneous solution. So the homogeneous, see here also you can see this is C is called the particular solution, and this is called the homogeneous solution. Homogeneous solution is nothing but once you make the equation equal to 0 after removing the 3 part, okay, the constant part, then if you solve this, then that give the particular solution by these 3 and the parameters here. Okay. So now in time series, what we do is that we introduce operator called lag operator. or some textbooks will call it as back operator. Okay, so where L is the lag operator. So if you multiply it with yt, then you will get yt minus 1. See, this lag operator is, if it is taking the value 2 here, then it is nothing but the second t minus 2. If it takes the value 3, then it is yt minus 3. So if I take, I replace this with the lag operator. Okay, here I have to keep Lyt. Here I have to keep L square Yt. Okay, if I do that, then I'll get an equation like this, which is very similar to the polynomial equation, quadratic equation. Okay, and then we have to derive the solution for the quadratic equations. Okay, so now in this framework, have solution of homogeneous and particular solution like this. This will be the homogeneous solution. This will be the particular solution. This is same as how we calculated the C, 3 by 1 minus these parameters. Okay. But these part, how it actually, in time series, it is little more complex than this difference equation, because we are going to deal with stochastic, where the error component is also going to come here instead of this intercept and all this. There is one more stochastic component will also be added to this. Then it becomes a stochastic difference equation. Solving that, okay, requires some level of mathematics to it, but as of now, don't worry about all this. But you have to keep in mind is that in the modern view of time series analysis, time series data, a particular variable is considered as an autoregressive process. Okay, and then it has to be solved using difference equations. Okay, so if we take this part as a polynomial and then try to get the solution of this is actually the solution. And also, mathematics, we also call it as root of this equation. If this part is greater than 0, then we'll have a root which is real and unequal. If it is exactly equal to 0, then we have roots, the real root and equal roots. And then if it is less than 0, so if any negative value comes inside a square root, then it becomes a complex root. Okay. But the idea is here. The idea is that the time series variable is considered a data generating process. Okay. What do you mean by data generating process? See, if there is a sales or production, say for example, there is a factory which produces cars. Okay, so there is a Ford company in Chennai which produces cars. So there is a capacity for any factory. So only if the capacity is 100, say for example, then it can produce a maximum of 100 cars in a month. Then what happens is that there will be some fluctuations in the production. Not necessarily every day factory can produce 100 cars. There will be some fluctuations because of many reasons, availability of the inputs, availability of the laborers. In a mass way, if laborers went on leave, then obviously there will be a problem in the production. And if there is another technical issues like, the power is not there for a couple of days, then there will be a problem in the production. So the capacity means the fullest possible extent that factory will produce if every resources are employed in a better way, but not necessarily every month they are going to produce the same numbers. So there will be fluctuations in the outcome. So time series has been viewed here as an outcome, which is actually coming out of a factory and which has a capacity. So the outcome may be anything, right? So the factory capacity is 0 to 100, say for example. So that is the set. So the outcome will be coming out of this set, any number out of this set. But if Ford adds one more unit to the factory, okay, so then the production goes up to 120. Now, the data generating process is something which is similar to the factory. Okay, so if it adds one more unit to the factory, which also has the increased capacity, now it can produce 20 more cars because of that new unit. Then, so up to a particular month, the output, the production has been produced by a single unit. And after a particular month, it is going to be coming out of that both the units. Then, in time series, this data, which is coming out of two different time point because of two different data generating process, right? Can't be compared, okay? Because the production which happens with the additional unit is totally different from the production happened with single unit. Okay, so in the modern idea of time series is that it is not the data which is coming out. Here we are more concerned about the data generating process. Okay, so first we have to see that whether the process remains stable or not. Okay, if every year, if Ford adds one more unit to the production, then obviously, you can't compare the output because the production, the output generating thing itself is different. So you can't compare these things. So what here what we do is we are more concerned about the data generating process rather than the data itself. Okay, so in the modern view, there are two things we have to keep in mind. The first thing is that it has been considered as a autoregressive function. Then it all becomes difference and differential equation problem. Okay, so that is the first part. The second part is that here the data generating process is more important than the data itself. Okay. So here there are predominantly in time series analysis of any economic variables, we have there are number of data generating process. Okay, predominantly we use two type of data generating process. One is random process. A random or stochastic process is a collection of random variables ordered in time. Okay, and a stochastic process is said to be stationary if its mean and variance are constant over time. A random process is called stationary process. See, the idea is very similar to what the example I have given to you. So we have to see the stability of the process in the sense that whether the process which produces that data is same or not, whether it's same over time or not. Okay, so if some new unit is added, then obviously there is a shift in the process. So that should be accounted into when you're trying to understand the time series. So a process is said to be stationary if its mean and the variance are constant over time. So why this is an important thing in time series analysis is that only for stationary things, where the process is stable over time, we can implement all the techniques. If it is not stable, then we can't use the methods which has been created for time series analysis. So you can't use Box-Jenkins methodology, which you will be, learning in the afternoon session, if it is a non-stationary process. If the data has been generated from a non-stationary process, then which simply boils down to which is a totally unstable process. Okay. Unstable means what? It's not a same process. Something else has been added at a time point. Okay. The other process which we are using here by most of the economic variables are random walk process. The stochastic process, which is said to be non-stationary random walk, if its mean and variance are varying over time. Okay, so that's the simple process is called stationary when its mean and variance are is non-stationary when its mean and variance are varying over time. And it is called random process. If it is not constant, then it is called random walk process. So there, as I told you, there are different data generating process which are there, and mostly it is used in other science subjects because there also they try to understand the time series thing. See, the time path of a particular atom. Okay, so if you really want to understand the time path of a rocket or the satellite, most of the time science people also use these kind of techniques to trace the time path of the object. Okay, for that, they are using so many different data generating process. There are different processes they use, but in our social science and economics, mostly we stick to these two process. Okay. So random walk again has some classifications. Okay. So without a drift means, see, I'll see this. Once you understand these two things, then the entire idea of stationarity and all those things are really easy. So if yt is a function of yt minus 1 plus a random error, then what happens is that y1, see, I'm actually trying to will be y1 plus u2. So I'm values here, it will be y0 plus and so on. So if I do that, yt will be nothing but y0 plus summation of ut. Take the mean of that ut, that yt, then I'll get the initial value, which is a constant. Okay. So for a random walk without drift, the mean of that series might be constant, which is not changing with respect to time, but the variance will be changing with respect to. If the random walk process has a drift means if it has a constant instead of yt minus 1, if it is constant, then tell you why there is no parameter before this yt minus 1. That is the key point you have to keep in mind. There is a constant plus yt minus 1. And if you take the mean of it, so we'll have t times the drift part as the mean. So again, it's a constant, but changing with time. So t element is there. So this mean the random walk process with the drift as not having a stable or mean and variance. It has a changing mean and changing variance. Okay, so pure random walk will be something like this. If p equal to 1, then the root of this equation, see, this is a difference equation. The homogeneous solution to this equation will be, 1. So yt minus yt minus 1 equal to 0. So if I take the lag operator, 1 minus L equal to 0. If I solve for L, I'll get 1 as value. So if you have a solution or the characteristic root of that difference equation becomes 1, then we say that there is a presence of unit root in that system. If there is an unit root, it obviously represents the random walk process, which is a non-stationary process. Okay. There are, again, we have, instead of, the drift, you can also have here. If it is this, then we'll have a trend stationary process. I'll explain it to you when I show some example for this. Okay. Now, the whole idea of the time series is this. Before coming into this unit root test, we'll go to the Excel to show you what it means, how we can generate random process and random walk process. You see my Excel file?
Yes, sir.
Okay.
Yes, sir. It's clear, sir.
What I have done here is that I'm going to use the same thing. So I'm going to pick a random number from the standard normal distribution. Okay. So here, if you see, so this uses the same function, and this is again, random number. So I'm randomly picking numbers from the standard normal distribution. That's it. So if that is the case, then we have data points. I've randomly picked 250 data points, okay, from the standard, which actually represents the random process. So if I actually plot it, the plot will be looking like this. If you see, you can observe from here itself that it actually roams around the 0 value because it's a standard normal distribution. If you see that, it won't breach 3, it will breach somewhere here, but only 1% will be greater than the value 3 because of one standard deviation. If you see that between one standard deviation, you can identify most of the 68% of the values lying in that range. 95% will lie in that 2 standard deviation thing, and beyond 3 standard deviation, only 1% will be lying. See, this is a random thing, so for every click we will get a new value, but everywhere you can see the same thing. But here what I am going to do here is I'm going to create y as a function of some value like this right, like this, rho yt minus 1 plus ut. This itself is a rho as 0.5 here, multiplied by yt minus 1 plus I'm actually creating another random this actually a kind of series of past value rho into past value plus ut. The next data point will be again okay, sorry. So as an initial value t, this is a function where we have given y0 as 0, and after that this is nothing but rho times yt minus 1 plus ut. Okay. So every time period there is a new ut coming, but this yt minus 1 is multiplied with this part. So if you see, if the rho is less than 1, value here, it is less than 1, 8, you can see that it roams around the mean value. I have drift 5 as an initial value. Okay, and also sorry, can have a drift here that it roams around, sorry. Roams around some mean and same thing. But the interesting point here is interesting point you have to keep in mind is that if the row becomes 1, okay, the row becomes 1, then it becomes random walk without drift. Okay. See that here if it is less than 1, then you take any time period. So you take the slice here, then calculate the average and the variance. It will be 0 and 1. Take this slice and calculate mean and variance. It will be 0 and 1. So you can take any slice in this time path and calculate the mean and variance. It will be 0 and 1 because it has come from the random process where the mean is 0 and if you want to, rather than drift, if you want to give instead of standard normal, you can also give equation. So here, normal equation will also we have to give the mean. If I give the mean as 5 and standard deviation as 0.5, that's sorry. If I give the mean as 0 and stationary means it should move around the mean with the constant variance. But if the row value takes the value 1, then what happens is that if I take any time slice here and then calculate the mean and variance, it will not be the same. So, so if it becomes exactly one, then what happens is that walk process. If the row value is one, it becomes the key idea you have to keep in mind. Interestingly, if I give a value which is slightly higher than one, the process totally becomes exponential. Instead of positive values, if I give a negative value like minus 0.2, then it remains as stationary random process. Minus 0.6 also remains as stationary. Totally becomes a different process. Here, if you take any time slice here and calculate the mean and variance, the mean will remain 0 for any point because there is a positive value and the negative value, but the variance is totally different. So this is another process which is actually kind of sound wave, which is used in the science than us. So the key point here is that if it is one, it's a random walk. If it is less than one, if it is greater than one, it becomes exponential. So at the negative side, if it is greater than one, it becomes something totally different. Okay. If it is minus one, this is again a different thing. And this, but less than one, then it is a stationary. So here there are the same process can be converted into a different thing based on this row value. So since we have only two cases, random process and random walk, in most of the unit root test, what we have is trying to examine whether this row value is exactly equal to 1 or less than 1. Okay. So there is, see, I'm not going to explain all the unit root test available. I'm going to explain only two tests, which is very popular. And every other test is actually an extension of this test only. So the basic idea remains same. We have to test whether this row is 1 or not. Okay, so instead of testing the row as 1 or not, what Dickey and Fuller has done is that in any regression analysis, rather than testing for a particular value, testing for 0 is very easy. Most of the regression analysis is or not for a particular value. Okay. To do that, same equation, what they have done is you actually subtract yt minus 1 on both the sides. Then you will have a value here like this. So this is nothing but the first difference, change in yt. Delta is nothing but rho minus 1, yt minus 1. Okay, so if this is 0, then what happens if this is 0? Rho is equal to 1. Right? So because rho minus 1 is nothing but delta. So if this is 0, rho is equal to 1. If this is minus some value, then if it is minus 2, then what happens? Rho will become minus 1. If it is some positive value, then it will be less than 1. Okay, so what we are trying to do is that we are going to see in Dickey-Fuller test, what we are going to do is that whether it is, if it is 0, then we conclude that the series is non-stationary because rho becomes 1. If it is different from 0, then we have to see what is the value it takes. Depending on that, we have to see. But the interesting thing is that if this becomes 1, positive 1 or greater than 1, then rho becomes greater than 1. If it is greater than 1, then the series is an exponential series. If it is greater than minus 1 also, it becomes a totally different series. So we have to keep in mind that Dickey-Fuller test only test for 1 or between minus 1 and 1. Okay, so that is the, if you go to the details of it, they are going to test only the modulus of this value. Okay, so that it remains there, because from this test we can also tell whether the series is exponential series or not. Augmented Dickey-Fuller test is nothing but using all the other things, and then also the past values of the first difference thing here, so that it becomes more robust. All the autocorrelation and if I include the lagged values of this, lagged values of the dependent variable, then it becomes more robust, the interpretation. So the basic idea is this: we are going to test whether delta is 0 or not. That's it. Then that will be telling us the story about the unit. Because if delta is 0, see, delta is nothing but minus values. Okay, so minus 1, minus 2, this delta we can do Dickey-Fuller test here. What we have to do is see if this is exactly 1, then if you see that, I'll take the first difference of this. This will be the to run a regression between these two.
Sir,
Yeah,
sir, not clear, sir. Hello, sir.
you can see table, right?
No, sir, we are seeing, it's an Excel thing, sir. Excel table and graph.
Voice is not clear.
No, sir, voice is
Okay.
breaking, sir.
This first difference, and this is the past values. So you have to run a regression for this. You can go to data. y and yt minus 1. So if you want to keep the lagged values of delta yt, then you can take these as lagged values and then include in the analysis. But I'm actually running a simple Dickey-Fuller test. Okay. So see if the value is p-value is not less than 0.05, so this remains 0. So it is we have to accept the null. Null here is this coefficient, delta coefficient is 0. Okay, so here if it is 0, obviously this series is a stationary random walk series. Okay, if I put 2 here, then you know the Dickey-Fuller T statistic will be something similar to the T statistics, but they have their own table to interpret. We can't simply interpret from these P and P values, but fine. So if it is significant, you know, obviously it tells that we have to reject the null of delta equal to 0, which means that the series is a random series, stationary series. Okay. So I
Hello.
stop here. Yeah.
Sir, you said that the ADF test, in ADF test, the unit root null is the unit root, that there the series is a unit root. The
No,
series
unit
contains.
root. See, yeah, unit. See, this is the series. The row is row should be 1. Okay, if row is 1, then the series is random walk, unit root process. Okay, but we can't test directly like row as 1 using a regression analysis. That's why we are slightly modifying the equation. Fuller actually modified the equation like this. Okay, so instead of testing row equal to 1, now what we are doing is we are testing delta equal to 0.
Okay.
Okay, so if delta is 0, then automatically it reflects that row is 1. So then the process is a random walk process. Okay, if that has been rejected, then you know it's a stationary process. So what the Dickey-Fuller statistic will give you is nothing but the similar T statistics of this regression. The p-value and other things will be derived from their Durbin-Watson table. They have created another table to do that. Fine. So I'll stop here. So if you have any questions, quick questions, we can have it so that I hope the time is up.
Yes, sir. Thank you, sir. Participants, you can post the question in the chat box. Have any questions, you can post in the chat box. Participants?
See, there are some questions, suggest some good books. See, two things I also tell to my students in the class. The books are like, you know, see, everyone has a different preference. Uh, which author you like? If I ask you a question like that, some people might like, even in novels, some people might like Dan Brown, some people will like Chetan Bhagat. Okay, so there are difference in preferences. Why you like that? No, it's our something which is very interesting to you, the way they write or something, the style they write. Okay, so the same thing is for the textbooks also. Okay, why there are so many books to explain the same concept? The same thing. So Gujarati might be telling the story. The econometrics remain same, but the way they tell they give the explanation and the way they explain things might be totally different. So I never refer any book in my classroom also, I'll ask people to go to the library and pick which is convenient to read for you, because every individual has their own way of listening to things. So whichever author,
Hello, sir.
yeah.
Sir, can you please appreciate the difference between the pure random walk and random walk without drift? You already explained that, but I want
Yeah.
to let it know further.
No, random
In
walk.
terms, yes,
Pure
sir.
random walk is nothing but the row equal to 1. That's it. Okay. So if the row is 1, exactly equal to 1, then it is called pure random walk. You might have a drift or without drift. It depends on the, see, everything comes from the random process. I'll tell you. See, the random walk process is nothing but the cumulative sum of random process. Okay. The cumulative sum component is the row component. If you are summing cumulatively the random process with less than one parameter, then you are going to stick to the same random process. But if it exactly equals to 1, it becomes a random walk process. If slightly above than 1, then it becomes an exponential process. Okay, so it all depends on that coefficient row. So the point here is that pure random walk is nothing but the coefficient is random walk itself is when the coefficient is 1.
Okay, the sum of
Why
okay,
there is
sir,
a word? So okay, the confusion is why there is a word pure. Okay. Right. So the point here is
yes,
that the value is 0.99. That row value is 0.99. Theoretically, it should be a random process. Okay. But if you look the graph, I'll show if you want. You see my screen, right?
Yes, sir.
Yeah. So now see this point, if I put 0.98, okay. The problem is theoretically, if it is less than 1, it should be stationary. Okay. But here, if the coefficient row value goes nearer to 1, then it will look like random walk. Okay. So now what happens here is that theoretically it's a stationary process, but it has all the characteristics of a random walk process. We call this as a fractionally integrated models. So the pure comes because to distinguish this and 1. Okay, so this also looks like a random walk, but this is the pure random walk. This is theoretically. But there is a class. See, if you go a little further into time series analysis, you might be all these series are called integrated series because it's all cumulative sum. If you cumulatively sum the random process with coefficient 1, it becomes a random walk. So since we are cumulatively summing, we call it as an integration. And this again is, it's called a fractional integration. Yeah, I've not explained this, but the pure word comes only to distinguish this fractional integration with the pure integration. Okay, pure happens only when the coefficient is exactly equal to 1.
thank you, sir.
Okay, so anything else? Series analysis, we need to perform unit to ref. Okay, what are the other mandatory terms? See, actually, there is nothing like. See, all the other things comes after this. The stationarity is to identify from which process the data has been generated. Okay, if you say the series is stationary, means the data has been generated from a random process. If it is non-stationary, then it means it has been generated from a random walk process. So there are different set of techniques to analyze the stationary process and different set of techniques to analyze the non-stationary process. So that will help you to pick the technique to analyze further. So all the other things like autocorrelation and heteroscedasticity in high frequency data all comes later. Okay, so we need to do all these examinations also. So that comes later. So in the afternoon session, I think you might be learning a little bit more on that. So what are all the other things we have to take care to do the time series analysis? If there is another question like drift is nothing but intercept. So see, there might be a case where the series is stationary around a constant. Okay, so that is also called stationary process because it comes with a constant as mean. So if a process roams around 5 or 10, then that is also a stationary process, but we call it as an intercept stationary. Once you remove that intercept from the data, it actually becomes a stationary series around mean 0. Okay, and also there is another thing called trend stationary. So as we said, trend is a function of time. So you draw a straight line, and then around that, if there is a process which is moving around that. See, actually, in the classical decomposition, what we have seen as y variable is actually a trend stationary variable. Okay, so you can use the modern techniques to understand whether that y which we generated in the classical framework is stationary or not. That is again a stationary series because it is moving around a trend. But it also see, and also another point I have to tell you that all these stationary process are also called mean reverting process. Okay, so they will come back to mean after a time. Okay, so you can see that the good thing about stationary process is this. It comes, see, we know that after a particular time period, it comes back to mean, okay, and then go back. So if I am here, I know that at what time period it come back. These processes are all called mean reverting process, but random walk process is not mean reverting. Might come to mean after a long period. Say for example, there will be some period where it might see it comes back to mean, but we don't know at what time it comes back. We can't predict the time at which come back to mean. So it may not come back to mean also. So random walk with drift, without drift, you have to include that into the regression itself to find out the if the drift parameter and the trend parameter also significant along with the delta parameter, then we can say that it is intercept stationary or trend stationary. What if our data fails stationarity? Then we have to use something different techniques. You can't apply the same, see, the Box-Jenkins methodology is meant for stationary series. So since non-stationary series is a cumulative sum of stationary, if you take first difference of non-stationary series, it will become stationary. Then you can use the methodology meant for stationary series. There are some methodology, which again, I'm going to explain tomorrow at the same time on co-integration and other things, which is meant for non-stationary series. Okay, so we have to use those techniques for those type of process. Okay.
Yes, any more questions? Okay, if you don't have any questions, we can close it. Induja?
I would like to take this opportunity to thank our speaker, Professor Sedu Dure sir, for the enlightening presentation, which gave us an introduction and valuable insights into the time series models. The examples and the application was highly informative and useful. Thank you, sir, for giving us so many points to ponder upon. With that, we will be concluding this session, and the next session will be at 2:30.
Thank you. Thank you so much for inviting me and patiently listening to me.
Thank you, sir. We'll meet tomorrow, sir. Thanks a lot, sir.
Bye.
Okay, we'll meet at 2:30. Be on time.
Sir, 2:30, which session, sir?
Sir, you're here. I'm sorry, sir. I didn't notice it.
No, I'm here only. In between that, since I am operating here only from my house,
Okay,
so in between some internet issues.
yes, sir. Actually, afternoon we have a Arima model, sir, from Sardaj Rasul from Bitsbilani, Dubai.
Okay. 2:30, sir. Okay.
Yes, sir, 2:30, sir.
Okay, sir.
Thank you,
Thank you,
sir.
sir. Thanks.
Good afternoon, Sardaj. Hi, Sardaj. Am I audible?
Yes, very good afternoon, Dr. Balaji. I hope I am audible.
Yes, Sardaj. How are you?
I am good. I am good. Thank you so much. How are you?
Yeah, I'm doing good. Just 5 minutes. People have to join. Okay.
Okay. Thank you so much. Am I audible clearly?
Yeah, you are loud and clear.
Okay. Thank you.
So, what's the time now?
It's 1 o'clock here.
Oh, had your lunch?
No, I had some snack
Okay,
somewhere.
I think you're disturbed on your lunchtime.
No, not an issue because I generally have a little late my lunch, and I had some around 12 o'clock some snacks. I went to canteen and had some snacks.
Okay, Sardaj. We'll start by just 2 minutes. Okay. I'll just post in the group.
No issues. No issues. So, Professor Raja has completed.
Yeah, sir finished on basic of time series models. He talks about random walk, unit root and all. So I think there is no need to cover that part again. So you can directly proceed to the ARIMA.
Fine. So this presently there's a break going on.
Yeah, actually the break is for 1:30 to 2:30. Probably people will join in another 2 minutes.
Okay, so it's a lunch break, huh?
Yeah.
Then I can understand. Participants will be back now, and they're really sleeping more.
Actually, we have
that happens after lunch everywhere in whatever part of the world. This is true, everywhere.
It's a good afternoon, sir. Can you hear me?
Yes.
Yeah.
Yes,
so, sir, are you going to use any software for this, or you are going to share your data only?
No, I will not.
No
use any
softwares, ma'am.
Okay.
No softwares. Actually, it's
So
only.
we will
as I
not
said,
have any hands-on practice.
Yes, ma'am. Why? Because we have a problem of copyrights. Okay, unless until we don't have softwares. If it's a non, it's fine. Basically, we have to give the records. So generally, it's not advisable to use the software because of the copyright issue. Even the resources may have the softwares, but you may not have that thing. That's the problem.
Yeah, that's the case.
Sardaj, actually, we have to handle 3 sessions a day. So morning 2 and the afternoon 1. So that 2 class every day. So little complicated for persons to be present on time. That's the issue, actually.
No issues. That is okay. We can understand because people will be really.
Yeah, we'll start in another 1 minute. Yes. I just posted the group, so they will join it very soon.
No issues because they will be tired by now, right? So then law of diminishing marginal utility prevails, and slowly people start getting tired.
Okay. Induja, are you here?
Yes.
Yes, sir.
Yes. Okay, we'll start. Let them join after some time also because yes, Induja, you can proceed.
Okay, so let me share my
90 participants are there. Obviously, yeah. Sardaj, you want to participants to switch on their cam or what? What's your
no issues. I don't think that is necessary. I don't think that's necessary. So still, it's up to them. Like if they want to, they can.
Generally, they won't. That's the issue.
I mean, that I think you should. I think you might have had. You will be having some clear policy about this. So whatever they are.
Yeah, actually, we are recording it. So for sharing purpose, it's required. But sometimes depends upon the resource person's convenient. We are lenient also.
I am okay. Yes, I have no issues because I think we are doing it for now last almost 2 years now. So I have got habitual of talking to a machine or computer. I can now I simulate a situation where I feel like as if I'm in class and then keep on going. But still, it is difficult as whenever we do it online, engagement becomes difficult. That participation of the students or those participants is highly appreciated because that helps us to be engaged and deepen the learning and understanding.
Yeah, fine. Okay, Induja, we can start.
Okay, so thank you so much.
Just introductory notes, Sardaj. That's nice.
A very good afternoon. I welcome you all to the fifth session of the online FDP on data analysis using econometric models. I would like to welcome our speaker, Dr. Sartaj Rasool sir, who is currently working as an assistant professor in the Department of Humanities and Social Science with Pilani, Dubai campus. Prior to that, he worked as an assistant professor at the Madras School of Economics from 2014 to 2017. He has a PhD in economics from Pondicherry University on the thesis on the anatomy of inflation, an MPhil in economics from Pondicherry University, and a master's in economics from University of Kashmir. He was awarded the Indian Council of Social Science Research Doctoral Fellowship and the Professor M.J. Manohar Rao Young Economist Award for the year 2017. Now, to talk more about the univariate time series models, I invite Dr. Sartaj Rasool sir.
Thank you, Induja. Thank you so much for these kind words. I really appreciate it. Thank you so much. And also, let me thank Dr. Balaji for inviting me to this session and deliver a talk on univariate time series forecasting. I really appreciate it. So let's first start with basic understanding of this topic or this univariate time series modeling. How many of you are aware about the concept univariate time series modeling? Have you heard it before ever? Are you having any basic understanding of the topic?
Sartaj, it's a heterogeneous group. Only those who are in economics, they might not know that, but the group belongs to commerce, management, and then some engineers are there. So it's a completely heterogeneous.
Okay, so let me then have kind of the holistic approach. I will go with basics, then slowly try to introduce you the various steps or states of this univariate time series modeling. Okay, let me start with what we might have discussed in the previous session quickly. Like there are different time series processes, or we also call them data generating processes, theoretical data generating processes, such as white noise process. And I hope you all know what are the properties of white noise process. And then we have also stationary stochastic process. As you know, Dr. Balaji was telling me that these concepts have been already covered in the previous session, so I will not discuss much of it. Then you might have also discussed what is non-stationary time series variable or what is non-stationary series. Then finally, we have also random walk process and different versions of random walk process. I'm not going to discuss anything about it. We'll move to our main topic, that is univariate time series modeling. Okay. Now let's ask a few basic questions. What is univariate time series model? What is a univariate time series model? Which kind of model is called univariate time series model? Can anyone tell me? Yes? Yes? No? You can type your answers, yes, no, in case you are not comfortable in speaking. Can anyone tell me what's univariate time series model? Yes?
You can respond. You can go ahead, participants.
Sir, is it a simple linear regression?
Okay. Simple linear regression. Anyone else?
Sir, analysis only by single variable.
Okay. Okay, great. Anyone else?
Moving with the same mean and variance.
Okay, that's a kind of a property of a time series variable. But
time series with equal time interval for a long period.
Okay.
Time series model for with only one variable.
Exactly. So basically, a univariate time series model is a model where we use only one variable to forecast the future values of that particular variable. So generally, when we understand theories, right, for regarding any variable, what do we try to understand? We try to understand what are the different factors which cause changes in any particular variable. For example, GDP, gross domestic product of a country, or growth rate of GDP. When we try to understand various theories related to determinants of GDP, we come into terms like investment, like there is investment, there is saving, there is what we call as population, workforce. technology, all these factors are discussed when we talk about what are the determinants of gross domestic product, right? Now, thing is, when we try to model gross domestic product in that framework, what do? We use the information on all these variables like investment, population, land, labor. All these factors are used to determine the value of GDP. So when we estimate a regression model with all these factors, we call it a multivariate regression model because there are a number of factors involved in forecasting or modeling growth rate of an economy, like investment, labor, capital, right? All these factors are information on all this data on all these factors is used to determine the growth rate of an economy. Now, this is a simple way to forecast growth rate of an economy. We can sometimes follow an alternative approach. As researchers, we are always restricted by data. We are always, we don't have ample information on investment. We don't have ample information on labor force of a country. We don't have much information on technology in a country. So we don't have much data on all these factors. Then we think like, is there a way that we will use data on growth rate to predict or forecast the values of growth rate in future? Can we have a technique where the data on only one particular variable is needed to forecast or extract information from that particular variable about its future value? Is there a technique? Yes, that technique is what we call as univariate time series model. As I said, univariate time series model is a model where only one variable is used to forecast that particular variable's future value. We try to model or forecast the future values of the variable in question. How? By using the information contained in that particular variable and then try to forecast or predict its future value. So in univariate time series model, only one variable is involved and the model is used to forecast or predict the future values of that particular variable. Now, why it has become so famous? The simple reason. Why it has become so famous? For the simple reason that it is simple. You don't need to collect data on various factors which determine growth rate. You simply need data on growth rate. Then you try to extract information from this particular variable in order to predict its future values. You don't need data on investment. You don't need data on labor force. You don't need data on technology. You don't need data on land or whatever. What are all those factors which determine growth rate? You don't need data on that. And also, sometimes these theories, these theories also are very, very contradicting. One theory tells us growth is determined by capital. Another theory says that no, growth is not determined by capital. Labor is important. Some other theory says no, it's technology which is very important. Some other theory says no, it is basically investment which is important. So sometimes theories are not clear. Then, as a researchers, we get confused. Which variable are relevant and which variables are not relevant? Then again, okay, forget about this theoretical part, these determinants. Can we use data on GDP in order to forecast the future values of GDP? The answer is yes. That's what we do in univariate time series modeling. Now, why has it become so famous? Why do we do univariate modeling? What are the reasons? What is the logic behind univariate modeling? First, as I said, it is less demanding in terms of data. Second, it is simple. Third, we can avoid the confusions which can arise from theoretical understanding. As I said, there are n number of theories proposing n number of variables telling us that growth is function of a number of factors. And we are not sure which factor is important, which is less important, which is more important. Then eventually we end up using we get confused and we end up using some irrelevant variables. So to avoid all that confusion, or to keep things very simple, we can use univariate modeling, as it is simple and it is less demanding in terms of data. There are some more important reasons for this logic behind or rationale behind why should we use univariate modeling. Okay, this that reason, those reasons which are responsible for this have a lot to do with the nature of time series of a variable. Can anyone tell me why you think a univariate modeling can be appropriate in a time series framework? Can anyone tell me? What are those features, or what are those distinguishing features of time series variable which makes univariate modeling an appropriate tool for the purpose of forecasting? Yes, can anyone tell me? Yes.
Uh, So because, see, for example, we are using the univariate analysis in finance. So suppose I am taking the share price data of one particular stock. So the movement of that share price in stock, it will be more dependent on the behavior of that company, its models and all those things, rather than correlating it with the external factors which are not going to impact too much on the stock. Yes, the volatility will be there because of the market or systematic risk will impact on it, but ultimately it is a own share price which will help us to predict the behavior in future. So univariate analysis is more appropriate in those type of data sets.
Okay, so you said like external factors. I can say when we talk about stock, we can talk about internal factors, factors related to company. Okay, share price of a company. There can be internal factors also. Then why can't we use internal factors? I mean, like, did you get my point? What I'm trying to say?
Yeah, so internal factors, we are actually, internal factors are impacting the stock price to some extent because this is based on the business model. But normally, if we are analyzing the data pertaining to the share prices, it is more about the behavior of that stock in a particular, you can say, framework for a longer period of time, rather than these you can factors which are impacting the price movement. These are occasional.
Okay, yes.
This is what I think. These are occasional. Say, suppose all of a sudden you have invited investor in your company. You just think about the Reliance. The moment others have outside parties and started investing in Reliance, and the Google or Facebook all have to. All of a sudden there was a change in the share price. Otherwise, it is impacting by its own behavior. It is having its own growth prospect. So for the prediction, we can use that univariate data to some extent. This is my understanding. Yeah.
Okay. Yes.
Can I add something?
There is some noise in the background.
Can we minimize the residual component?
I think I must think over here. But
ऑन द गो हाँ नहीं तो 4:30 बजे के बाद बहुत देर हो जाती है सर
Devika, can you please mute your mic? Everyone please mute your mic, and the person who would like to speak, then during that time only you can unmute your mic. There's a lot of noise coming in the background.
Sir,
Yes, someone wanted to add something.
Can we minimize the errors or residual term impact?
Okay. I mean, that we do in regression model also, right? We try to minimize errors in order to extract all explainable information or explainable component of dependent variable while extracting information from independent variable. That we do in multivariate model also, right? Minimize the sum of squared residuals. That's what we do in multivariate model also. Yes. Yes, Ajaz, you can add something. But it would be good if you speak, because I am not able to follow the chat because I am on slide mode.
the question was,
It is breaking. Your voice is breaking.
Incorporate. Hello, sir. Am I audible?
Yeah, somewhat. I'm sorry.
The question.
I'm really sorry. You are not audible.
Ajaz, your voice is breaking, man. Better you can post it. Maybe he will answer after some time. Your voice is breaking. Ajaz?
Okay. So I said why univariate modeling can be appropriate, particularly in time series modeling, is because of the fact that the time series variables have certain distinguishing features. They have certain distinguishing features which are not there in case of other types of data, cross-sectional data, or some other types of data. So time series variables have certain distinguishing features which enable us to use univariate modeling to forecast its future values. Now, what are those certain basic features? That will justify why univariate modeling is very attractive, why is it commonly used, why, what justifies its use. Okay, it is basically the nature of a time series variable, the way time series variable is generated, how series is generated over a period of time, what are the features of this, distinguishing features of this time series variable, which makes univariate modeling appropriate or more suitable. Okay, one important feature of time series variable is possibility of autocorrelation. Okay, what do we mean by autocorrelation? Can anyone tell me what is autocorrelation? Yes.
Correlation of the present values with the same variable of the past values.
Okay, the correlation of a variable with its own past values, right? How the past values of a variable are affecting the current values of the same variable. That is the correlation or association between the past observations and current observations of a time series variable. So the tendency of a variable being influenced by its own past values. Yesterday's value is affecting today's value. Today's value is going to affect tomorrow's value. So this typical feature is generally present in time series variable. That is that current observations or observation in period t is being influenced by some past observations, maybe in t-1 or t-2 or t-3. Some past observations have significant impact on the current outcomes of this particular variable. So that's what we call autocorrelation, the presence of autocorrelation. The past observations having tendency to influence the current observations of a particular variable. That's what we say, what we call as autocorrelation. That is one important feature of time series variable. You can see this present in almost all the time series variables. Let's talk about growth rate of an economy. If a country is having higher growth rate in the period t-1, it may have higher growth rate in period t as well. And the growth rate in period t may determine the growth rate in period t+1. So there is a strong association between the current observations and the past observations of the variable which we are talking about. So that's one important feature of time series variable. So that tells us, that gives us an information or idea that the past observations may have some information about future values or future observations of this variable. So that means past data can be exploited. Past data can be exploited and used for predicting future values of this particular variable. So that's one important reason why univariate makes sense, because the past observations are the values of the past values of a particular variable has some information content about future outcomes. Why not to use it? Why not to understand what yesterday's data point has to tell us about today's data point? What last year's growth rate has to tell us about this year's growth rate. So we try to manipulate that. We try to extract that information by realizing that past observations have some impact on current outcomes, right? What next? Like another important feature is that time series variable is also influenced by past disturbances, or you can call them past shocks, right? So how do we define shock? Can anyone tell me? What is a shock in time series context? Yes? Can anyone tell me? Okay, you can say no, you can type no in case. Am I audible?
You are loud and clear, Sardash. You are clear.
No, I think I want to hear this from audience, because that
Okay.
engagement is
No, actually,
important.
I unmute all. That's what sometimes they are in the position to unmute, because to avoid the noise, I mute all. That's my wish.
They're in a position to know, they can speak right whenever they want.
Yeah, they can unmute themselves. They can talk.
Okay, yes, guys. How do we define a shock in time series variable?
Sudden drift, or is it sudden drift? Is it to the lower end or the higher end? Where a particular event actually creates the immediate change. That what I meant by immediate change, the drastic change in the value of a particular variable.
Okay. So in simple words, you are right. In simple words, we define shock in time series variable as a sudden or unpredicted change or deviation of a variable from its expected value or from its mean value, right? So a sudden or an unpredicted change in a time series variable from its mean value, when it deviates from its mean value or expected value, and this deviation is unpredicted, it is not predicted, we call it a shock. So sometimes time series variables face shock. They undergo a shock, and this shock may have impact on the future values of time series variable. Now, we need to understand these shocks can be, like, for example, I will give you an example of a shock. We are talking about agricultural production in India. Okay, we have a data on agricultural production in India for last 20-30 years. Now, let's assume that last year we had a bad monsoon. Okay, it created a disturbance, a sudden change in agricultural production, and agricultural production suddenly fell down by certain percentage, and it reduced from the expected value by certain percentage. Now, what has happened? A poor monsoon has caused a shock in a time series variable, that is agricultural production of India, right? So sudden change, and the value of agricultural production has gone below the average value or below the mean value. That is a shock. Now, this deviation, sudden deviation in agricultural production from its mean or expected value may have an impact on future agricultural production or on this year's agricultural production. That is also fact. That's also true, because a shock, even though this, we know that this a shock in agricultural production due to a drop in rainfall, is basically a temporary shock. We know it is a temporary shock. It is a transitory shock, but still, because of fall in agriculture, poor monsoon, the agricultural production of this year may be also influenced. Because of disturbances in agriculture, because of fall in incomes of farmers. They may not have enough money to purchase fertilizer for a certain period of time, or for this year at least. They may not have sufficient income to invest in their farms and produce high yield seed. So because of the previous shock, their incomes might have reduced, and with the result, the current year's production has also got affected, even though in the current year we had good monsoons, right? So this previous disturbance is going to have impact on the current outcome, or this year's disturbance is going to have impact on future outcome of agricultural production, right? So previous disturbance, the impact of previous disturbance on current outcomes, or the impact of current outcomes, current disturbances or current shocks on future outcomes, is another important fact of a time series variable. Now, here we need to understand the difference between the shock, which is a transitory, short memory shock, a transitory shock, a shock in agricultural production due to drop in rainfall or due to poor monsoon, is basically a transitory shock, because its impact will die. It will die, and it will be a transitory impact, but the shock will have impact. There can be also a shock which is a long memory shock. The impact of that shock does not die out. It remains there. Okay, it remains there for a certain period of time. It continues there. Like, I will give an example. A person facing, let's say we're talking about productivity of an individual. Now, unfortunately, this particular individual has met an accident, a shock, right? It is a shock in his it will bring a shock in his productivity. Okay, because of this accident, his productivity is going to change. It is going to fall drastically. Right now, this accident, is it going to have a temporary impact or a permanent impact on productivity? Yes. Is it going to have temporary impact or permanent impact on the productivity of individual? Yes.
It depends.
Yes. Is it going to have a permanent impact on productivity or a temporary impact on productivity?
Generally, can be temporary.
Intensity.
Yes.
So depending on the intensity of the accident,
I said his productivity, let's say he became handicapped.
so then it is going to impact on the productivity.
Exactly. So basically, now this shock is a long memory shock. The impact of this shock is not going to die, it is going to remain there. Okay. So then in time series variable, there's a tendency that a previous shock may have a transitory impact or a previous shock may have a permanent impact. When we say transitory impact, we are saying the shocks are, this particular shock is of a short memory shock. There is a short memory shock. And if the shock has a strong and permanent impact, okay, then we say that this time series variable, productivity of an individual over a period of time or over his age, is also a time series variable. You can think about a heart rate, an individual having a heart attack at certain age, unfortunately having a heart attack at certain age. Okay, now you can think about whether it is a temporary shock or it is a permanent shock, whether it is a long memory shock or it is a short memory shock. Okay, so that means now in time series variable, the previous shocks can have significant impact on current outcome, and the current shocks can have significant impact on future outcome of that particular variable. That's also another important fact of time series variable, right? Third important thing, that's also interesting feature of time series variable. It has a trend. Can anyone tell me what do we mean by trend in variable? Yes. Can anyone tell me what do we mean by trend in variable? Guys, please respond.
So like, what is the general movement of the data along the different years? Like, if we are talking about GDP, what is the movement of GDP in different years?
Okay. Okay.
In a long-term perspective, either the data, the values are increasing or decreasing. That is the trend value on a certain proportion, which can be measured in univariate.
Okay. Yes. So the presence of trend in time series variable implies that the time series variable has a tendency to increase or decrease at some constant rate over a period of time. The time series variable has a tendency to increase or decrease at some predictable rate, or at some, what shall I say, linear rate over a period of time. Like, for example, you take about the height of an individual. The height of an individual has, from childhood till his old age or till 30 or 40 years of age, it has a tendency to grow at some constant rate over a period of time or at some predictable rate over a period of time. That is what, if a variable has tendency to grow, you do anything or you don't do anything, but the variable will grow over a period of time. As time proceeds, it will grow. It has a tendency to grow at certain rate over a period of time, or it has a tendency to fall at certain rate over a period of time. So that is what we call as the presence of trend. Take an example of, suppose you are measuring the growth rate of any particular plant over its lifespan. Tree. This tree has a tendency to grow at certain rate, certain predicted or certain, what shall I say, known rate over a period of time. Similarly, the time series variables. It has been observed that because of the various economic circumstances or because of the economic conditions, the various economic time series variables have tendency to grow at some certain rate over period of time, at a certain rate over period of time, or they have a tendency to fall at a certain rate over period of time. So the tendency of a variable to change with time, nothing changes, only time changes. We proceed over period of time. The tendency of a variable to change with time at a certain rate is called a trend. Now this trend can be positive if variable is growing over period of time. It can be negative if variable is falling over period of time. Or in case of tree, it is positive because the tree has tendency to grow over period of time at certain rate, right? So similarly, you can think about the crime rate in a country. As country becomes more civilized, more better, it becomes more and more developed. The crime rate has tendency to fall over a period of time. So you will find a negative trend in crime rate in the growth history of a country when country grows over a period of time, right? That's what we say top trend. Now this trend, again, it can be because of complications in time series variable. This trend can be deterministic, it can be stochastic. What do we mean by deterministic and stochastic trend? If trend is predictable, if we know at what rate it is going to grow over a period of time, we call it predictable trend because we can estimate it. We can use the data and extract what is that rate over which it will grow over a period of time. Then we say trend is deterministic or predictable. But sometimes this trend can be stochastic, random. We may not be able to predict at what rate this particular variable may grow over a period of time. Sometimes it may be growing at certain rate, and other times it may be growing at some different rate, and some other time it may be falling at certain rate. So we see a random trend in a variable, a stochastic trend in a variable. So generally, what we can, the information which we can use or the information which we can extract from a time series variable is only the deterministic component, not the stochastic component, right? Another important factor or another important feature of time series variable.
So can you please repeat the last statement, whatever you have said, the last statement?
The last statement about trend, I said that the component which we are bothered in univariate time series variable is the deterministic component, the component which we can extract, the information which we can extract by understanding what kind of trend it has, by estimating the trend component of a variable and use that component to forecast the future value of the time series variable under question. We are not bothered about the deterministic component because that is not predictable, because that is a random component, the random trend in a variable, which becomes difficult for us to predict or estimate and extract from a given variable in order to use it for predicting future outcomes or future values of the variable, right? Is it clear, Rahul?
Yes, sir. Yes, sir.
Okay, now another important factor, feature of time series variable, which also justifies why a time series variable may contain a lot of information within itself. A time series variable has a lot of information about its future outcomes or about its future values. Okay, all these factors. One more factor is this seasonality or periodicity. Okay, what do we mean by seasonality of a time series variable or presence of seasonality in a time series variable? Can anyone explain? It's also called periodicity. Yes, can anyone tell me?
It has same trend at a particular time period.
Okay.
For example, in the 10 years period, for all the first quarters, it has increasing, and all the second quarters, it has decreasing, the same kind of movement.
Okay. Anyone else? You can speak. This platform is for discussion. Let's express ourselves. No one is going to judge you. No one is going to evaluate you here, but it will help us to keep discussion engaging. So please.
The change in the value of the variable with the change in the time, like for example, it can be the winter. For example, the sales in the winter. It can be with respect to the summer. So it's actually looking at the time changes, the event changes, simultaneously the variable value changes.
Exactly. Thank you, doctor. So basically, seasonality implies in a time series variable, it implies that the time series variable has tendency to behave in a certain manner at regular time intervals. At regular time intervals, at some regular time intervals, the variable has tendency to behave in a certain predictable manner, in a certain predictable manner. For example, the prices of cotton cloth, prices of cotton cloth across different seasons in a year. So during summer, the price of cotton cloth is generally predicted that it will be high. During winter, the price of cotton cloth is expected to be low. Why? And this will repeat. This cyclic behavior will repeat every year. Every year at regular time intervals, that is at summer, during summer and during winter, the price of cotton cloth is expected to be high and low respectively. And this behavior will reoccur continuously every year. When a variable has a tendency to change continuously at regular time intervals, in a certain predicted manner, we say it has a seasonality. That it contains a seasonal component. That is tendency to change in a predictable manner or in some certain manner at some regular time intervals. Here time intervals are summer and winter, right? Similarly, you can think about other time series variable. I will give an example, which I went to workshop for one medical college, because they also use a lot of time series data for forecasting. So then I was like, thinking what time series data they are mainly using. They try to forecast the heart rate of an individual, how the individual heart rate is going to change. Okay, so basically these doctors also deal with a lot of time series medical data. Okay, so now this time series heart rate of an individual measured over a period of time is a time series variable. Now let's assume that this particular individual has a kind of habit of going gym every day morning. Every day morning, this person has a habit of going to gym every day morning. Then what do we observe? What we will observe in heart rate? What we will observe in this time series of heart rate? Yes. Generally in gym, people work out, they run.
The heart rate will be high.
So you will observe that over a period of time, every day at certain time in the morning, the heart rate of this patient goes up. It goes up every day during maybe, let's say, 7 to 8 time between this time interval. It goes up and it is above than the average value. It is above than the normal heart rate. It is above than the normal heart rate, right? And this happens every day continuously. This behavior in heart rate, that is being above average every day, it occurs every day in the morning. Then we say that there is a seasonality in the heart rate, because heart rate has a tendency to increase at certain has a tendency to be higher than the normal heart rate during certain time intervals over lifespan of this individual. That's an example of seasonality. You can also think the reverse. When we sleep during night, naturally or biologically, the heart rate has tendency to go low during night, because we are not active, we are not doing any workout or any exercise or anything. We are not moving, we are lying on bed. During heart rate in midnight, during midnight time, generally our heart rate is below the normal heart rate or below the average heart rate, because we are inactive, right? So what happens again, when we measure the heart rate of this patient over a period of time, let's say over last 10-15 days, right? And we know we may measure heart rate per minute basis, right? Per minute basis. The frequency is minute by minute. So you see when during night time, the heart rate of this patient dips below average. It goes down below average, and this reoccurs every day. This happens every day. Seasonality is that it reoccurs every day. The pattern is continuous and regular during the same time interval. And then we say again, there is this seasonality in the heart rate. right? You can think about a number of examples in economics also. As I told you, one, prices of cotton cloth, prices of wool cloth, or prices of agricultural products. There's a season of harvest. Remember in Tamil Nadu when there is this this harvest of mangoes. During harvesting season, the price of mangoes goes down. During every year during that particular season, the price of mangoes goes down, and it has been observed from ages. And when there is that off season, the price of mangoes is generally high, and this has been continuously happening. So the price of mangoes to behave in certain predictable manner or in certain manner at regular time intervals, at some regular time intervals, is what we call as seasonality. Is it clear?
Yes, sir.
Okay, another important factor which justifies why a time series variable may contain significant information about the future, about its future values, about its own future values. That's structural break. What is a structural break in a variable? There is structural break in a relationship. There is a structural break in a variable. You should know the difference. Suppose X and Y are related, and this relationship is, let's say, a linear up to a certain point of time, and after that particular point of time, the relationship becomes non-linear. Then we say there is a structural break in the relationship. Okay. Then let's say a husband and wife, they have a relationship. Okay. After marriage, up to a certain point of time, they don't fight. So there's a linear relationship. After that first fight, when it starts, and that becomes so ugly and so bad that the relationship changes after that particular fight or that particular day, when that ugly fight happens, the entire relationship changes. So that's the shift in relationship. Similarly, do X and Y are related in certain manner, maybe a linear manner, up to 2000, let's say 10, and beyond 2010, X and Y are not related in a linear manner. They are not related at all, or they are related in some different functional form. Okay, non-linear form. Then we say there is a structural break in a relationship. Then how do we define structural break in a variable? Yes, I'm talking here more about structural break in a variable. Yes. Am I audible? Say yes, no.
Yes, sir.
Yes, sir.
Thank you so much.
So when there is a change at a particular point of time in the data, so can we call it as a structural?
Come again, Tripura. Please come again. I didn't hear completely.
There is a change, abrupt change or sudden change at a particular point of time in the data set or in the flow of the data. Can we call it like that?
Yes, you can say when there is a change and then this change is permanent. This change in permanent. A time series variable is said to have a break if at some point of time there is a change, and after that this change is permanent, and the time series variable does not go back to the old path or old trajectory. It remains now at some different trajectory. The path it follows is completely different after break. Like for example, we have a company and the CEO is very risk averse person. Is very risk averse person, does not like taking much risk. So then we have this price of share of this company that is growing up in a certain manner over a period of time. Now the company changes the CEO. Now some aggressive behavior CEO has been brought in. He is very risk lover. He enjoys taking risk. He's very volatile. Now what has happened? The stock price is still changing, but now it is changing in a different manner. The stock price or the share price of this company has taken a different path now. It is changing, but it is changing entirely in a different manner. What does it mean when I say it follows a different path after break, or it changes in a different manner after change? That means the mean and variance of this variable will be different now compared to the earlier period when there was a risk averse, a stable CEO of a company. The share price was growing and it had certain mean, it had certain variance. Okay. Now, after new person has been brought in, there's a change in management. Now, the mean and variance of this variable is entirely different. That has changed. That has changed to some different level. the path of the variable has completely changed, then we say that the variable has a break. The variable has a break. Take an example of performance of financial sector of US till 2008-9 financial crisis. So we can measure the performance of financial sector of US economy till 2008-9. It had certain different mean, different variance. Because that time we were reckless. We were the financial sector was reckless. They were more aggressive. They were risk lovers. No one bothered. No manager of the bank bothered. Everyone was recklessly lending. Now, after we were hit by financial crisis or financial meltdown of 2008-10, now if you measure the performance of financial index or the financial performance of US financial sector, if you measure the performance, it's entirely different. Its mean variance of this variable beyond 2010 onwards is entirely different. And what do we say? That there is a structural break in this variable. Is it clear? Again, justifying us that the time series variable can undergo certain permanent changes over a period of time, implying and telling us that sometimes past observations may not have necessarily all the information about future outcome, right? These are some important distinguishing features of time series variable, which help us to understand, or which motivate us to use time series modeling to understand the fact that the information contained in the past observations of data can be used to predict future outcome. The past observations, the information the information contained in the previous observations can be used to predict the future outcomes of particular variable or future observations of a given variable. All these features highlight that fact or underline the fact. Hence, when we understood this fact, why not to go for univariate time series modeling?
Sir,
Yes.
in the case of structural break, no, sir, as you said, it is following a new trend because of something. So in that case, can we use the past data to predict the future? What is it, sir?
Interesting question. Now that depends on, are you talking about data before break or data after break? So if the data before break will be irrelevant, because as I said, the complete path of the time series variable has changed. But if you are restricting yourself using data up to that break, okay, the recent past, yeah, of course you can use. Did you get my point?
Yes, sir. Because what I got is, as you said, after the break, your data is completely changing. Like your mean is changed.
So if a time series variable
can be predicted with the help of the past. That is my question, sir.
Exactly. If the observations are the observations from the period which are before the break period, no, they have no information. If the observations which you are using to predict the future outcome are from after the break period, that is, they are from the recent past values. The values are recent past values. They contain information about future. Those data points are from the period which is after the break period, are obtained after the break period. They have information, but no, the data which the observations which are there from the before the break period, right, before 2008-9 financial crisis, they may not have sufficient information about the future trajectory of this particular variable, because as the variable has undergone a structural break. Clear?
Thank you, sir. So, but the structural breaks cannot be predicted, no, sir. We don't know when
we can only incorporate them. We can only incorporate them. Okay. We can only incorporate them in the variable, but we can't predict.
Okay, sir. Okay. Thank you, sir.
Okay. Now, let's move to some basic concepts of univariate time series modeling. The concept which I am going to discuss now is very important. It's very important from the perspective of understanding the anatomy or the crux of univariate time series modeling. Okay, there are two important concepts: autocorrelation and partial autocorrelation coefficients. Okay, let's discuss these two concepts in a simple manner to understand what partial autocorrelation coefficient tell us about the behavior of time series variable? And similarly, what partial autocorrelation coefficient tell us about the future observations of the variable or about the behavior of time series variable? Okay, have you understood these terms before so that I can then move fast, or you have not understood? Yes, no. The question is multiple choice. Yes, no.
Understood, sir.
The partial autocorrelation, just can you give one time explanation? Partial autocorrelation.
Okay, let me explain you these two basic concepts. They're very important concepts in time series modeling because, as I said, they give us a lot of information about the behavior of time series variable. Right? Let's assume a scenario. I will ignore for a moment. We are talking about time series. Let's assume a scenario where x is nothing. It is the growth rate of China. Okay, then I have z variable. It is nothing but the economic growth rate of US, right? Then I have another variable y here, which is nothing, economic growth rate of UAE, United Arab Emirates, right? Now here I am assuming a situation or a scenario where I'm saying that x is function of z. That is, I'm saying that the growth rate of China is dependent on the growth rate of United States, right? And I'm also saying that the growth rate of UAE is also function of the growth rate of United States. Z is nothing, it represents growth rate of United States. So I am saying that growth rate of China is function of growth rate of United States, and growth rate of UAE is also function of growth rate of United States, right? Now, let's assume also that, that this growth rate of China is also independently related to growth rate of UAE. That is, X is also independently function of Y. So whether United States is there or not there in the scenario, the growth rate of China will be influenced by the growth rate of United Arab Emirates. That's why. So Chinese growth rate is also is independently or is independently correlated or is independently influenced by economic growth of United Arab Emirates. That's what this equation tells us. So this is an independent relationship here, right? Now, what do we mean by partial autocorrelation coefficient, right? So to understand that, we are then saying, then when I understood x is function of z, that is growth rate of China is function of United States, growth rate of United Arab Emirates, y is function of United States, and I also assumed that the growth rate of China is also function of growth rate of United Arab Emirates. That is, China and UAE are also correlated through strong trade relations, right? Now, therefore, I can simply say that that x, that is growth rate of China, is basically a function of two variables. That is y, that is growth rate of United Arab Emirates, and growth rate of US, that is z, right? That's how I can relate it. Now, how I will model this relationship? Suppose I want to estimate this relationship. I will write it in an estimatable form, which is given here. This is an estimatable form of this, which is given here, right? Now, here, if I determine this relationship in this manner, right? And I am interested in understanding how growth rate of United States is affecting the growth rate of China, right? I am writing the relationship like this, and I'm incorporating also another variable y. That is, I also know that growth rate of China is also affected by growth rate of UAE. So I am incorporating also y here. Now, what I am doing here, when I am trying to determine what determines how the economic growth of China and economic growth of United States are correlated, I am at the same time controlling the impact of growth rate of UAE on the growth rate of China. That is why impact of Y on China is also controlled. Impact of economic growth of United Arab Emirates on the growth rate of China is also controlled. That's also included in the model. Controlled means the impact of that particular variable is included in the model. Right?
Hello.
So it is included in this model. Yes, someone is speaking. Hello, hello.
Who is this?
Sir, this side Ankur Jain. Actually, I want to know, sir, it is about univariate. Is there any partial autocorrelation in univariate series as well? Here we are taking Y and Z.
I will come to the end. Let's understand first concept in a simple manner.
Just a minute, Sadaj. Participants, you can pose the questions because it will disturb the flow. Okay.
So basically, I will first make you explain what is autocorrelation, partial autocorrelation in general sense. Then I will bring it in the context of time series. Okay. Is it clear?
Yeah, you can proceed, Sadaj. Yes.
Okay. So now I am here interested in examining what determines growth rate of China and and how is it related with growth rate of United States. That's what I'm interested in. And now I specified an equation like this, where I am saying growth rate of China is a function of United States growth rate, of course, but it can be also influenced by growth rate of United Arab Emirates. So I am incorporating Y variable also. So the impact of growth rate of UAE on growth rate of China is also controlled, right? Because the variable economic growth of UAE is included in the equation, right? Now, then what is this rho 2? That is this rho 2, what does it indicate? What does it measure? Okay, if it measures nothing but what we call as partial autocorrelation coefficient. That is the impact of economic growth rate of US on economic growth of China. While the impact of UAE's growth rate on China is controlled, that is given by rho 2. So it is a partial impact of the growth rate of this UAE as growth rate of United States on growth rate of China. So this rho 2 measures nothing but partial autocorrelation coefficient, or we call it partial derivative. It is the partial derivative of x with respect to z, right? If you take rho x by rho z, that will be rho 2. Then what is rho 1? Rho 1 is again partial autocorrelation coefficient with respect to variable y. So this gives me partial autocorrelation coefficient with respect to growth rate of UAE. This gives me partial autocorrelation coefficient with respect to growth rate of United States, right? And x is nothing, economic growth rate of China, right? So then, as I said, partial autocorrelation coefficient relationship between the growth rate of China and growth rate of United States is given by rho 2. This is the partial autocorrelation coefficient. Similarly, the partial autocorrelation coefficient of impact of growth rate of UAE on growth rate of China is given by rho 1. It is given by rho 1. So then we say rho 1 is the partial autocorrelation coefficient with respect to y, right? Now, what is then autocorrelation coefficient? Now, this growth rate of United States can affect growth rate of China, not only directly. That's what we have tried to extract here. The direct impact of Z on X. The growth rate of US on growth rate of China. That's what we have extracted by calculating rho 2. It calculates the direct impact. The growth rate of US can also affect the growth rate of China through the growth rate of UAE, because of the strong relationship between growth rate, because of the strong trade relation between UAE and United States. What happens when growth rate of United States increases, the growth rate of UAE also increases. And when the growth rate of UAE increases, that will cause increase in growth rate of Chinese economy as well. So that means the economic growth of United States can affect the growth rate of China in two different ways. One is through direct impact, that is impact of Z on X. Also, the Z can affect, that is economic growth of United States can affect Chinese growth rate through its impact on Y. We call it indirect impact. So when United States grow at a high rate, UAE also grows at a high rate. When UAE grows also at a high rate, then it will cause higher growth rate in China as well. So Z may also affect X through changes in Y, because Z can trigger changes in Y and Y can trigger changes in X. That's called indirect impact. Z can have an indirect impact on X through United States. That is through the economic growth of United States. That's Y. That is Y. And then when you calculate the direct impact, as well as indirect impact, that means you are considering autocorrelation coefficient. Autocorrelation coefficient estimates both direct as well as indirect impact of economic growth of United States on the economic growth of China, right? That's what it calculates. And we call it, we have in mathematics, we have a name for it, we call it total derivative. The total change in X with respect to change in Y and Z. So Z can independently affect X. Z can also affect X by causing changes in Y, and Y can affect X. So Y can change mainly because of changes in Z, and that when Y changes, it will trigger changes in X. That's called indirect impact, right? So we then specify, if you calculate a simple regression like this, you're trying to understand the change in how economic growth of China is determined by economic growth of US, that is Z. You estimate a simple regression like this, then this row 2 captures autocorrelation coefficient, not the partial autocorrelation coefficient. It controls autocorrelation coefficient. That is, it captures the total change in X with respect to change in Z. And this total is summation of two impacts, direct as well as indirect impact. Here, this equation is different from this equation. This model is different from this model. Can you tell me how? How is it different? Yes? Yes? If you model a Chinese economic growth like this, or if you model Chinese economic growth like this, what is the difference? As I said, row 1 will give you partial autocorrelation coefficient, row 2 in this will give you partial autocorrelation coefficient with respect to Y and Z respectively. Here, row 2 will give you autocorrelation coefficient, ACF, autocorrelation coefficient with respect to growth rate of Z or with respect to growth rate of United States. What is the difference? The difference in two equations or in two models is only that this model controls the impact of Y on Z. The independent impact of this model controls the independent impact of Y on Z, or how Y independently affects Z. That impact is controlled through partial autocorrelation coefficient row 1. However, this model does not control the independent impact of Y on Z. It's not controlled. So that's why it's a total impact. The independent impact of Y on Z is not controlled. So we say, if you measure an equation like this, let's say, X is function of simply Z, growth rate of US is simply a function of growth rate of this United States, then this will measure total impact, and we call it autocorrelation coefficient. If you measure equation like this, okay, then we call row 1 as partial autocorrelation coefficient with respect to Y. This is partial autocorrelation coefficient with respect to Z, right? Is it clear? Fine. Now let's bring the concept in our framework, right? Now we will bring the concept in our framework. Here, let's assume that YT, a time series variable, economic growth of a country, is function of its own past values. That is, YT is function of its own past values. There is lag 1 variable, this is lag 2 variable, this is lag 3 variable, and I can have T minus 1 up to any lag. So I'm saying the growth rate of India is function of its own past lagged variables or lagged values. right? Now, assuming this, now suppose we are calculating an partial autocorrelation function. If we want to calculate partial autocorrelation function, we will write it like this. This is an example of partial autocorrelation coefficient, where when you estimate this equation, rho 1 will give you partial autocorrelation coefficient with respect to t minus 1. Rho 2 will give you partial autocorrelation coefficient with respect to t2, yt2, and rho 3 will give you partial autocorrelation coefficient with respect to yt minus 3. That's lag 3 variable of y. Lag 3 variable of y. These are partial autocorrelation coefficients. That is your trying to estimate the impact of some past observations on the current outcome of y, while controlling the impact of observations which fall in between intervals. While controlling the impact of observations which fall in between intervals. That's what we do in partial auto. This is a partial autocorrelation function or equation. Right? This is at lag 1, lag 2, lag 3, lag 4. Now, autocorrelation coefficient, right? Now, we know that yt is function of all these variables, but I'm simply saying yt is function of yt minus 1. I estimate equation like this. I'm ignoring this. Let's say I is here 2. I'm ignoring t minus 1. I'm ignoring t minus 3 variable. I'm ignoring t minus 4, t minus 5. Are they ignored? I'm simply estimating function that yt is function of some function of yt minus I, where let's assume I is 2, it is t minus 2. That's I'm saying yt and yt minus 2 are correlated. That's what I'm assuming. And rest I'm not taking anything into consideration. That there can be other lagged variables of yt which can also affect yt, that those variables are not taken into consideration. Now, if I calculate this, that is total change in yt with respect to t minus 1, it gives me total derivative that is given by gamma, and this is generally non-zero. This is generally non-zero. Okay. However, for white noise variables, this gamma is nothing. It is an autocorrelation coefficient here. Gamma is nothing. It is an autocorrelation coefficient with respect to, let's say, I is equal to 2. It is with respect to t minus 2, yt minus 2. So autocorrelation coefficient with respect to this variable is gamma. Similarly, if you take t minus 3, then it will be gamma 3 or gamma, whatever you name it. You can denote it through different terms. So actually, there should be subscript here j, so that it shows it changes with respect to different lag variables. So I missed to put that j here and gamma j. Anyway, that I hope you understand. So note that this partial autocorrelation coefficient and autocorrelation coefficient are generally non-zero. They are generally non-zero for a time series variable. But however, there is a certain category of time series variables for which it is 0. Can you tell me for which type of time series variable the partial autocorrelation coefficients and the autocorrelation coefficients will be equal to 0? Yes. Can you tell me? Yes.
Non-stationary.
Okay. Non-stationary. Okay. Anyone else?
The mean values are 0.
Okay. What else?
Variance.
Okay, you might have heard discussion on white noise process. For a white noise process, all these coefficients, rho 1, rho 2, rho 3, rho 4 are 0. Similarly, lambda I, lambda 1, lambda 2, lambda 3, lambda 4, all these are equal to 0. All, that is both autocorrelation coefficients as well as partial autocorrelation coefficients with all the lags are equal to 0 for a white noise time series variable. Because we know white noise is IID, identically and independently distributed variable. That means past observations have no information about future outcome. Past observations have no information about future outcome. Every observation in each time period is independent. The observation in any time period t is independent of any other observation in the past. So every observation is independent of its own past values. So in that case, this does not make sense, because this will be equal to 0, meaning that past data has no information about future outcomes or future values of this particular variable. And for white noise, generally they will be 0. For non-white noise variables like stationary, they are non-zero variables. They are non-zero non-zero variables. So this, if I assume t minus 2, gamma will give me autocorrelation coefficient with respect to t minus 2 variable. Now, if I assume I is equal to 3, then gamma will give me autocorrelation coefficient with respect to yt minus 3. That's lag 3 of y, right? Lag 3 of y. Similarly, if I calculate with respect to yt minus 1, what will be that? What will be that? Generally, for the first lag, the autocorrelation coefficient and partial autocorrelation coefficient are same, because there is no data point in between that. There's no variable in between yt and yt minus 1. Yt minus 1 is the first lag. So when you calculate partial autocorrelation coefficient with respect to t minus 1, or with respect to or autocorrelation coefficient with respect to t minus 1, they will be same, right? I hope the concept of autocorrelation coefficient and partial autocorrelation coefficient is clear. Yes, here gamma gives with respect to t minus 1, you can calculate with respect to t minus 2, with respect to t minus 3. Insert a variable here, you will get autocorrelation coefficient. In this equation, the indirect impact is not controlled, or with partial, the total impact is considered. In this, the partial impact is controlled, or the impact of other variables is controlled in the model, but you are incorporating the possible impact of other variables. So that's why we call it partial derivative. This is a partial derivative. That is, while assuming that other variables may also change. In here, yes, yes. I think Anishka is speaking to someone else, not to me. Okay, now once it is clear the autocorrelation coefficient and partial autocorrelation coefficient, okay, now we can specify what we call as autoregressive model or AR model. Okay, here we assume that when we specify AR1 model, we assume that yt depends on its own past values. In AR model, we always assume. Yes, anyone wants to ask something?
Yes, sir. Can white
Participants,
noise?
please wait. Let him finish, because don't interrupt. It may be a problem for him. Let him finish, then you can post your questions. You can note the questions. Don't disturb his flow. Okay.
Sir, this discussion will over then if I am not saying is this time.
Dr. Balaji, I think let him speak. It's okay.
Sir, you mentioned in the previous slide the white noise process. Sir, can this white noise be similar referred as stationary?
White noise is stationary. White noise process is a stationary series. What are the properties of stationary series? That its mean and variance remain not zero. Mean and variance remain constant over a period of time. That is, the distribution of possible outcomes across each time period, it looks same or is similar. So
IID process.
Yes, the distribution of possible outcomes across each time period is similar, or their IID as they're similar, identical distributions. So hence mean variance of each distribution remains same over a period of time, and then we say a variable is stationary. So this is true for white noise. White noise is a pure stationary process.
Okay, sir. Okay, sir.
Is it clear? Because
yes,
what is white noise? It has zero mean, right? And it has a constant variance. It has a zero mean and constant variance. So white noise generally oscillates around zero. It has a no zero reverting tendency. Zero is its mean, and it has a mean reverting tendency. Hence, it is a stationary variable. A variable which has a mean reverting tendency. When it changes from mean, it has a tendency to come back or oscillate around mean. Which we call it that it is.
So that means the row value will not be equal to 1.
Root mean value will not be equal to
1.
Yes, that if it is not equal to 1, then that means it will be mean reverting. If it is equal to 1, that means the roots of this equation are outside the unit root. Hence, we say it is non-stationary. It does not have tendency to revert back to mean.
Okay, sir. If it is greater than 1, can we apply the techniques of time series?
Okay.
Like if it is greater than 1.
You are saying if no, it is greater than 1, what does it mean? So what is greater than 1
Mm-hmm.
mean? Like, what does it mean? If it is equal to 1, we are saying the past observation has full information about current outcome.
Mm.
The past observation has entire information about current or future outcomes when it is equal to 1. Being greater than 1 means what? The past
It is showing
observations
more
contain,
information.
wait. The past observations contain more than information, more than what is necessary information about the future outcome. So in that case, what will happen? This series will not converge. It will explode.
Mm.
Did you get my point?
Yes, sir. Yes, sir.
It will not converge. If it is greater than 1, then it will explode. It will be explosive series. A series which does not have any tendency to come back to mean, of course, but it is also very explosive series.
Okay.
And generally,
Okay.
does it make sense? Like, can we assume that in a time series variable, the partial autocorrelation coefficient can be greater than 1? Does it make sense?
No.
Because
There is
economic
a
time series variables are not explosives. They're not exploding. They don't explode over a period of time. If that behavior would have been observed, maybe we would have considered that. But generally, we assume that the series is not explosive series, or it's not exploding over a period of time. It is converging, right? Or it can be simple random walk process, where we say that past observation has a complete
Okay,
or
sir.
full
I got that.
information
Thank you, sir.
about today's outcome. The yesterday's value is
Sure.
nothing. Today's value is nothing. Yesterday's value plus some random change. That's what is random walk process, right?
Okay, sir.
Is it clear?
Yes, sir. Yes, sir.
Okay, thank you so much. So in simple AR process, we assume that we write AR process AR1 like this, where we are assuming that the past lagged one variable has impact on the current observations. We write it like this. Okay, here we are saying basically the YT is function of its own lag, but only one lag is considered, YT minus 1. We generate YT minus 1 lagged variable, and then YT with YT minus 1, and beta 1 estimates how strong is the association between lagged variable of Y and YT. Lagged variable of Y and YT. And here we assume that UT is a white noise process. It's a pure white noise process satisfying all the assumptions of classical linear regression model. Satisfying all the assumptions of classical linear regression model. All the normal properties, whatever they are. So this is how we specify AR1 model. So it is auto-regressive. That is, the variable is regressed on its own past values. That's why auto-regressive. Auto-regressive. The variable YT is being regressed on its own past lagged variable, which is YT minus 1. If only one lagged variable is incorporated, we call it AR1 process. That means only one lagged variable is used to generate YT, and UT is basically white noise process here, right? So if a particular variable is generated by a series like this, we call it is an AR1 process. Okay, take any economic data. Okay, then estimate a model like this. If you find that the predicted values from this model and the actual values are close, and they follow a similar path, or the forecasting error is less, then you will say that, okay, this variable can be categorized as AR1 variable. Like we can say GDP is an AR1 variable if this model or this equation is holding true. This equation is holding true. Then we say GDP follows AR1 process. We can also use AR2 process, right? Instead of including only one lag, you may sometimes require to use two lags. That is, now you are saying YT is function of its own lag 1 and also its lag 2 variable. It's lagged 2 variable, that's YT minus 2. Right? So now here we are in this equation, we are telling yesterday's observation is affecting today's outcome, right? And today's observation will affect tomorrow's outcome. That's what we were saying in this model. But here we are saying now today's observation is affected by yesterday's observation and also by day before yesterday's observation. then we're saying that today's observation is going to affect the tomorrow's observation as well. So basically, we're saying it is the past two lagged variables which are having an impact on the current observation. That's what we are trying to tell here. Here also, UT is a white noise process satisfying all properties of white noiseness. And this is how we can write A2 process. So A2 means there are two lagged variables of this variable incorporated in this model. And if a particular variable, when you, let's say you use exchange rate data and you fit a model like this, then estimate this equation, okay, and you find that UT is a white noise process, that's very necessary in order to understand whether this equation is an appropriate equation or not. We must ensure that UT is a white noise process. If UT, disturbance term, error term is not white, this equation makes no sense. It is not appropriate. This equation is not appropriate. This model is not appropriate. And you cannot call an exchange rate AR2 process. Only when you use exchange rate data, then generate lag 1 variable, then you generate lag 2 variable, right? Then you estimate this equation, estimate these coefficients. After that, check the properties of error term. You found that the error term is basically white noise process. It satisfies all the properties of white noise process. Then you conclude that the exchange rate is following AR2 process. That is, the exchange rate for a particular country is generated by this process, and you can use this process to forecast its future value. The basic purpose of ARMA modeling is to forecast the future value. Why are we interested in forecasting? Because we want to know the impact of any decision before that decision is taken. That's why forecasting is interesting. You want to know how the world is going to change or how the variable is going to change when the conditions are changed, when the decisions are taken, what are going to its influence. When I shifted from India to UAE, it would have been very informative for me to understand, and it would have been very helpful to know, hypothetically, as if I have gone, how my life is going to be there, right? That's what we call forecasting. How my life is going to be there before actually shifting to UAE. How my life is going to be there. If I knew this, I can make informed decisions. Similarly, if I know these things about economic variables, that how the variable is going to change, if this particular variable changes, how this variable is going to change in future, if this condition is changed or this variable change, then I can make better decisions. I can advise better policies. I can frame better policies because I know what is going to be the impact of this policy decision on this variable before actually announcing the policy. That means I can make a well-informed decision, or I can design a well-informed policy, right? That's why forecasting is important. That's why ARMA modeling is assumes very much importance in time series modeling. Then we have ARP process, a general model. Why only two? Sometimes time series variables may need more than two lags to model the particular variable. You may need more than 2 lags. Sometimes you may need more than 2, more than 3 lags, more than 4 lags. So you can have a general autoregressive model which is of order P. So you can expand it. It is nothing but yt is equal beta 1 yt minus 1 plus beta 2 yt minus 2 plus beta 3 yt minus 3 plus dash beta p yt minus p. So you can expand it like this. Instead of writing it in expansion, I simply took beta I out and wrote yt I minus like this. So you can expand it also, right? Assuming I runs from 1 to p, you can expand it also, right? So instead of writing a long equation, I what shall I shrink the equation by writing it in some summation form like this. Everything is made. So this is an AR of p order, autoregressive of p order. Now, here again I repeat, again we are assuming yt is function of its own past values. We are saying yt is function of its own past 2 lags, and here we are saying yt is function of p lags. P can be any. So depending on variable, we may need different number of lags for different variables to model it, to forecast it. Now, bringing that, we have taken into consideration that autocorrelation, that the variable may have autocorrelation. That's past observations may have impact. Past observations may have impact on current outcome. That we have taken out into consideration by incorporating simply lagged variables, right? When we are talking about distinguishing features of time series variable, Remember, we discussed certain reasons that time series variable may have autocorrelation. So previous values may have impact on current outcome. We incorporated that fact by incorporating AR term in this model. By using AR term, this is called AR1 term. This is AR1, AR2 term, right? So by incorporating the lagged variables in this equation, we considered the fact that the past observations might contain some information about future outcomes of this variable. Now let's take into account. Let's take into consideration now another important fact, that the one which we discussed, that past shocks may have impact on the current observations as well. Past shocks may have impact on current observations, where I discussed the impact of poor monsoon, right? Where I discussed the impact of poor monsoon, remember? Right? So past shocks may have impact on current observations as well. So here, then, in order to incorporate that fact that past disturbances or shocks may influence the current value of a variable, we write a model which is given like this here. I'm saying the current observation of YT can be influenced by shocks in period T minus 1. The agricultural production in period T might be influenced by the poor monsoon, or the disturbance or shock, or the deviation of actual agricultural output from its mean value. Let's say actual agricultural output is 80 less, mean value was 100 tons. So that is a shock, right? That's a deviation, that's a difference. Deviation, that 80 minus 20, that minus 20 is the 80 minus 100 minus 20 is the shock. That's the deviation. And that past deviation minus 20 may have impact on this year's production or this year's agricultural output. That's what actually I'm taking into consideration here. So the past deviation, the shock, the difference between actual agricultural output minus mean or average agricultural output, that may have an impact, right? So that's what actually I'm taking into consideration here by incorporating the lagged value of error term. UTI is nothing, it is an error term, right? How the error term is nothing, it is the difference between actual value minus expected value of a variable, or actual value minus estimated value of a variable is error term or residual term. That is a shock. I have estimated value or expected value, I have actual value. The difference between these two gives me nothing but shock, right? So I am using the lag value of error term, the disturbance term of a regression model. I'm using it here to incorporate the impact of past shocks on current observations, right? So it may not be necessarily that only previous shock is affecting the current agricultural output. Maybe there would have been some disturbance in the year before last year. In the year before last year, something would have happened. Maybe farmers were protesting, or some shock would have, farmers were protesting. They were busy in protesting across India. Then agricultural production might have reduced. The actual agricultural production would have been lesser than the expected agricultural production. Then there is again a shock in the last year. So now that protest of farmers in the year before last year might affect the agricultural production this year also. Maybe people forgot how to do farming, or people are still depressed. Farmers are still depressed, or they got distracted from their activities. So the protest or the changes happening in the year before last year can also affect the current agricultural production. To incorporate that, I am using the disturbance term, the lagged to disturbance term, or second lag of disturbance term as well in this model. So this incorporates the impact of previous disturbances due to poor monsoon, the impact of protests by the farmers in the year before last year. That's what this will incorporate, and I'm incorporating this, then writing MA model like this. I'm writing MA model like this, and it takes into account the fact that the current agriculture output might get influenced by previous year's disturbances due to monsoon, and the year before that, the disturbances due to protest in farming sector of India, and that can also affect the current agricultural output. right? That's what it takes into account. Here also UT is a white noise, is assumed to be a white noise process. Now here also in this equation, UT is assumed to be a white noise process. Now again, I reiterate that if in a particular, you estimate a model agriculture production like this, and you found beta 1 is statistically significant, non-zero, and UT, that is this disturbance term, the residual term, it is a white noise process, then you can say that agricultural output follows MA process. So if any researcher wants to predict it or forecast the agricultural output of India, he can use MA process. He can use this MA process, right? You can tell him that it's an MA process, it follows MA1 process, that is only one lagged variable of disturbance term is incorporated, that's why it is called MA1. So you can tell him it follows MA1 process. So that means if he is interested in forecasting the agricultural output of India, he will write an equation like this, generate a lag value of error term, estimate the equation, estimate beta 1, check whether UT follows a white noise process, yet it follows a white noise process, then conclude that the agricultural output follows MA1 process. Then another researcher may say, no, farmers, the protest of farmers in the year before last year also is having impact. Then he may suggest, no, MA2 is better. MA2 process is a better model for agricultural output in India. So then he suggests an alternative model, which is given by this, which has two lags of error term, which has two lagged variables of error term. And here also UT is white noise, assumed to be a white noise. So if UT is a white noise, then only this equation is appropriate. Otherwise, this equation is not appropriate. This is how we specify MA2 model. Two lags are included, the lag 1, lag 2. So that's why MA2. I can write a general MAQ model. MAQ model means there will be Q lags incorporated. Q lagged variables of error term incorporated in your regression model. So you are having now Q terms or Q number of lagged variables of error term incorporated in the regression. So it will be T minus 1, T minus 2, then beta 3, T minus 3, then beta 4, T minus 4, dash, beta Q, T minus Q plus UT. That will be the general model. So instead of writing that long equation, I can compress the equation by writing it in a summation form, something like this. So you can expand it. Say I is equal to 1, write beta 1, T minus 1, then that will be first term. Then say T is equal to I is equal to 2, then you can write second term, I is equal to 3, so on and so forth. You can go till lag Q, that is MAQ model, where Q lags of error term have been incorporated in your RIC model, right? Now, the fact is, more important fact is that a time series variable may be explained by both mix of previous disturbances as well as the previous observations. That is, time series may be represented as a mix of both AR and MA model, both AR terms as well as MA terms. Previous shocks are also influencing, previous observations are also influencing the current outcome. That is actually more realistic model. Then we write a model called ARMA11, 11 indicating that there is one term of AR, there is one lagged variable of AR, one AR term is incorporated, and MA1, another one represents there is also one moving average term. There is one moving average term incorporated in this model. MA is moving average term incorporated in this model, which is nothing but lag value of error term, incorporated in this model. So here we are saying that, okay, time series variable can be influenced both by past observations as well as past shocks. So then use ARMA11 model. That's what we are doing here. So you can also write ARMA22 model, which is written like this, ARMA22 model. It is written like this. Now it has two AR terms. One is this, another is this. It has two MA terms. One is this moving average, that is lag value of error term, and lag value of error term, second lag or second order lag of error term, which is given given by this. So this is called ARMA22 model. That is two AR terms are incorporated in the model, and two MA terms or two lagged variables of error term are incorporated in this model, right? This is how we specify ARMA22 model, right? So at particular, now which series a particular time series variable may follow, which particular specification a particular time series variable may follow, varies from one time series variable to another variable, depending on the nature of time series variable. Some time series variables follow simple AR1 process. Some follow complicated ARMA 2, 2, 3, 3, 4, 4, 5 processes, right? Now, I can write the general ARMA PQ model like this. So it has P terms of AR process, P AR terms, and it has Q MA terms. It has Q MA terms, Q likes of MA terms, and it has P likes of AR term in this model. It's a general AR MA PQ model, right? And as I said, it is written in a compressed form, don't get confused. Now, one thing we need to keep in mind when we embark on time series modeling, particularly univariate time series modeling, we need to understand the time series properties of variable. So how do we understand time series properties of variable? As you might have understood by now, that we try to check the stationarity properties of a variable. So you should keep in mind one thing, that ARIMA modeling is appropriate only when we assume that the variable which we are trying to forecast follows a stationary process. If it follows a non-stationary process, ARIMA modeling is not appropriate. Suppose a variable follows non-stationary process, okay? Then can we use ARIMA modeling for that particular model? No. Then what is the solution? So if a model is a non-stationary, we should first convert it into a stationary process. There are a number of ways to transform a variable from non-stationary process to a stationary process. Let's say I take exchange rate. Exchange rate can be a non-stationary process. But if I take rate of change in exchange rate, that may be a stationary process. That's the beauty of time series variable. Suppose I take price of a particular commodity. It may be a non-stationary variable. But if I take rate of change in price of particular commodity, that is the growth rate of price, the rate at which price changes, percentage change, that percentage change variable may be a stationary variable. Similarly, I can take GDP of a country. GDP of a country may be a non-stationary variable. But if I take the growth rate of GDP, the rate at which GDP changes, that is the percentage change in GDP, that may be a stationary variable. So GDP at itself may be non-stationary, but the growth rate of GDP or the rate at which GDP changes, when you calculate that change, the difference, right? YT minus 1, YT plus 2 minus YT minus YT plus 1, YT plus 3 minus YT plus 2. When you calculate the difference between two observations in two time intervals, that difference may be stationary variable. Okay, then if you are having a variable which is non-stationary, transform it first into stationary process, right? By simply using its first difference, logarithm form, any other form, whatever you want to use the form, convert the variable into stationary process. Convert the variable into stationary. Once the variable is converted into a stationary process, then you can use it for Riemann modeling. Let's say you are talking about GDP. GDP itself is a non-stationary process. Now, can you use Riemann modeling for GDP itself? No. Then what? You can use growth rate of GDP. That is rate percentage change in GDP. That is a stationary process. Then you can use Riemann modeling there. You can use Riemann modeling for growth rate of GDP, not for GDP itself, but for the rate of change in GDP. Now, for example, we are talking about GDP, and it is a non-stationary process. Okay, and we assume that it's an integrated of order 1. What do we mean by integrated of order 1? That when you take its first difference, the rate of change in GDP, that is a stationary process, right? Then we call it is integrated of order 1. However, if the first difference is not stationary, then you are taking the difference of first difference. That's called second order difference. The rate of change variable, the difference of a difference variable, difference to variable. So if you take the rate of change of growth rate, that becomes second order difference of GDP. First order difference is growth rate of GDP. Second is the rate of change in growth rate, right? Acceleration, that becomes the second order, what we call as second order integration, right? So if it takes one difference to convert a variable into a stationary process, okay, let's say in case of GDP, itself is non-stationary, but the growth rate is stationary. So it took us one difference to convert stationary variable into a non-stationary variable, right? Then we can specify the model for GDP as. Now we are not considering Y. Y was GDP. Now we are modeling del Y. Del Y is growth rate of GDP, rate of change in GDP, right? So that's what we are modeling here, right? So del YT is function of del YT minus 1, that is growth rate. Growth rate is function of its own past values. That's again growth rate. And I have disturbance term also here, right? MA term here, that is disturbance term, it is given like. Then we call this model is called ARIMA, that is ARIMA 111. One MA term, one AR term given here, one AR term given here, one MA term there, right? And it is integrated of order 1. That is, it took us one difference. It took us one difference to convert GDP into a stationary process by considering its growth rate. While considering its growth rate, so it took one difference. So we say it is integrated of order 1. So in this I represents the order of integration, and order of integration for this example GDP is 1. So I write 1 here. For some variables, the order of integration may be 2. Like you're saying, price. Price is non-stationary. You calculate inflation. Inflation is also non-stationary. Then you calculate rate of change in inflation. That is second order derivative, second order integration, second difference of this price variable. That may be stationary. Rate of change in inflation may be stationary. Then in that case, I will be 2. That is it takes you to consider two differences where in order to convert variable into a stationary process. You need to consider two differences, or you need to transform the variable into inflation first, price into inflation, then don't consider inflation, consider rate of change in inflation, the rate of change variable, right? Generally, in economic time series and financial time series, it does not take more than one difference to convert a variable into stationary process. So generally, most of the economic variables are integrated of order only 1. They are integrated of only order 1 generally. So here YT was GDP. Then I am modeling now growth rate of YGDP. Del denotes rate of change in GDP as function of its own past values plus some disturbance term plus UT, right? So this is called ARIMA. That is one AR term. There is one lagged variable of dependent variable. Then there is moving average term, that's disturbance term here also. So one, and there is this variable has been converted once. The first difference has been considered in order to convert this variable into a stationary process, and the transformed variable is modeled, not GDP. We are modeling here now growth rate of GDP, not the GDP. There's a difference. Suppose Y is price, del YT will be inflation. So we will be modeling here now inflation, not price, right? So that's what we are doing here. Right? So you can write a general ARIMA process like this, where this I denotes nothing. It denotes the order of integration, how much differences it takes you to consider to convert this variable into a stationary process, right? So D is a general word which is used. It can be 2, 3, 4. As I said in exam, generally D is 1. And you can write the general ARIMA process like this, which is written ARIMA. AR is the order of it, the lag order for AR terms is P, the lag order for MA terms is Q, and the order of integration is D. Order of integration is D as given here, and it is specified like this. If a particular variable takes one difference to become stationary, and there are two MA terms and two AR terms involved to forecast the variable, then we call it ARIMA 212 model. ARIMA 212 model, right? If it needs three AR terms and one MA term and one difference, we call it 311 model. ARIMA 311. So this is how we name these models. Now the question is, how do we determine lag structure? How many lags should we incorporate? How do we determine lag structure? That's the important question. Shall I have AR2 terms? Shall I have AR3 terms? Shall I have AR4 terms? Or shall I have MA1 term, MA2 term? Right? This order of integration we can easily understand. So once the variable becomes stationary, so stop there. We know we can easily determine D. But how do we determine the lag order of AR term and lag order of MA terms? So the simple answer to that question is, in a nutshell, when you estimate this equation, stop at a point where the sum of squared residuals, sum of squared residual term, that is this, is minimized. Keep on changing the order of this AR term lag structure and MA term lag structure. Keep on changing. Then choose the lag structure corresponding which the sum of squared residual is minimized. That is, summation of UT square is minimized. The model corresponding which sum of squared residual is minimized, that model will be the best model for the purpose of forecasting. That model will outperform all the alternative models in forecasting the time series variable. Why do we use the model, or why do we choose lag structure based on minimization of sum of squared residuals? Why do we do that? Simple reason. The model which generates minimum sum of squared residuals is the model which will be best, or which will be more accurate in forecasting the future values. So model which generates minimum sum of squared residuals is the most accurate model for the purpose of predictions, for the purpose of forecasting, right? For the purpose of forecasting. So now I hope you have understood all these basic concepts, or all these AR MA processes, and how do we determine model. So generally, we follow a proper procedure. We follow certain steps when we do AR ARIMA modeling. And that particular procedure which we follow is called Box-Jenkins decision tree. First, what do? We identify model. Okay, how do we identify model? We try to understand theory. We see how much lags of AR term are important, how much lags of MA term are important. That generally comes from theoretical understanding. Okay, once we determine the initial model, we estimate the model. Once you have estimated the model, then what do is we check diagnostics. What do we mean by check diagnostics? We check the properties of error term. That's very important. Once you have estimated the model, plot the residual series. Understand what are its properties. Is it looking a white noise process? Is it not looking a white noise process? If it is not looking like a white noise process, your model is inappropriate. If your residual term in your model is looking like a white noise process, or it satisfies all the properties of white noise process, then your model is good and you can go ahead for forecasting. You can use your model for forecasting purpose. However, in diagnostic check, when you check the properties of error term or residual term, you identified that the error term has certain issues. It does not qualify as white noise process. It does not satisfy the features of white noise process. The error term is not IID. It's not a random process. It's not IID, identically and independently distributed process. Then what do? We revise the model. We go back, revise the model, try to incorporate more AR terms, incorporate more MA terms, and then re-estimate the model, check again diagnostic statistics, see the properties of error term. If properties of error term are resembling the properties of white noise, then we start forecasting. Otherwise, we keep on estimating and re-estimating. So trial and error, we try to identify an appropriate model which will minimize the sum of squared residuals. Okay, so I have more details to present, but I think we don't have much time to go ahead. Dr. Balaji, can we continue, or am I supposed to stop here?
Yes, actually, it's time. So how many slides you have, Sardaj?
Actually, I have more, so it will take some more time there.
Okay, fine. As a basic idea, that is fine. We are giving AR and MA terms, though there is no need for extension and all. I think better we can stop, because
I have still 5 minutes. We can now have some questions or some discussions in case anyone has any query.
Yes, you can actually. Yes, just a minute.
Sir, yes, sir. Can you show you one example quickly in 5 minutes, whatever you had done in figures, so that we can understand it properly?
Okay. Yeah. Fine. No, I don't mind. I will try to see what I will not give you much details, because it it takes a lot of time to explain things. But still, I will see what extent we will be.
So one question.
Yeah, please.
Sir, like if I have a data of 10 to 12 years monthly data, so on that, can we do ARIMA model? Like,
Why not?
okay, sir.
Why not? It depends what type of time series variable it is. So, no, why not? You have high frequency, low frequency, that doesn't matter. The nature of variable is important. No?
Okay, sir. Okay. Thank you, sir.
So I have a question. I have data on GSDP of a particular state, and I want to forecast about it. But this COVID scenario, it is how we are going to deal with this.
So basically, you have one way is to just eliminate the, this abnormal time period. That is, you estimate your model till 2019 end. Yeah, 2019 end, December 2019, and just eliminate the abnormal period. Or you have another way is like, you incorporate a dummy variable for this last period. You can incorporate a dummy variable in order to, accommodate for this change, a structural change in an economy due to COVID-19 restrictions.
Okay, so
One more question.
Okay, so yeah, someone requested me to go through slides, but I don't think I'll be able to do so. Okay, yeah,
Yes,
please.
let him finish. Let him finish. Actually, then you can have a questions. Even I can help you with the questions. Let him finish the section. You have 5 minutes so that you can just slow the slides because they want to see what you're doing. So just show them, then we can wind up.
Okay, so the first thing when you want to do ARIMA modeling, first thing, but suppose you have variable Z, go to try to estimate partial autocorrelation coefficient and autocorrelation coefficient associated with different lags. That's the first thing you do. And in generally, if you use some software like we use eViews, all of us use eViews. So when in eViews, what do? We have a function called correlogram function. Okay, you just select a variable. Let's say it is GDP. Hit the button. It will say, I don't know, estimate correlogram. It will give you correlogram. It will tell you for how many lags you want to estimate partial autocorrelation coefficient and autocorrelation coefficient. Let's say you are saying 20 lags. For 20 lags, I want to estimate this. So you do these inputs, estimate. You will get a diagram like this, and this is what we call as it's kind of an X-ray for a time series variable. What does it tell us? It gives us information about autocorrelation coefficient and partial autocorrelation coefficient. AC is autocorrelation coefficient, PAC is partial autocorrelation coefficient. This is AC and PAC at lag 1. AC at lag 1, PAC at lag 1. I told you why AC and PAC are same at lag 1 in this lecture. I hope you understand that. Then this is autocorrelation coefficient for lag 2. This is partial autocorrelation coefficient for lag 2. This is lag here. In this column, we say lags. This is autocorrelation coefficient for lag 3. This is partial autocorrelation coefficient for lag 3. Now we have got these estimates. We need to test whether these coefficients are statistically significant or not. In order to test whether these autocorrelation coefficients and partial autocorrelation coefficients at different lags are they statistically significant or not, we do hypothesis testing and we use Q statistic to estimate whether PAC and AC coefficients are statistically different from 0 or not. Now, this is Q-stat and this is p-values associated with Q-stat. You can see that the p-values are equal to 0, implying that we cannot we cannot reject the null hypothesis. We cannot reject the null hypothesis that these coefficients are equal to 0. These coefficients are equal to 0. That means they are non-zero. They are non-zero. Their autocorrelation coefficient and partial autocorrelation coefficients are non-zero. Then what do we say? It's not a white noise process. If it is not a white noise process, that means we can forecast it. If it is a white noise process, that means we cannot forecast it, right? So here you can see the p-value associated with Q-stat given for different autocorrelation coefficient and partial autocorrelation coefficient at different lags. The inferences are same. P-value is closer to 0. That's we cannot reject the null hypothesis, concluding that this autocorrelation coefficient and partial autocorrelation coefficient are non-zero, or they are non-zero. And this graph gives us nothing, but it graphically reflects the the strength or the magnitude of autocorrelation coefficient, and this graph, these spikes reflect the graphically the magnitude of partial autocorrelation coefficient. Note one thing, that when these spikes associated at different lags or associated with different lags are outside these borders, then without looking at these numbers, you can say the autocorrelation coefficient is statistically different from 0. That is statistically different from 0. Similarly, a partial autocorrelation coefficient is outside this lag. You see, at lag 1, it is outside this zone. Again, you can say, like doctor says, okay, there is some issue with that particular bone. You can say, okay, partial autocorrelation coefficient is statistically non-zero. You can say that with confidence that it is non-zero, right? Partial autocorrelation coefficient, because the spike is outside this band. It implies the coefficient is statistically significant and hence non-zero. Right? So this is how what you can interpret. So this at this lag also autocorrelation coefficient is statistically significant. At this lag also autocorrelation coefficient is significant. You can see it is significant till for all 20 lags. Right? This is an information we can extract from this conogram. It implies, what do we conclude here? That yes, past observations have significant information or ample information about the future values of this variable. The past observations have significant information because the autocorrelation coefficient and partial autocorrelation coefficient both are statistically significant at different lags. At different lags, they are statistically significant or non-zero, indicating that the past observations have significant or ample information about the future values of this particular variable, right? That's what we can conclude here. Now, moving forward, then we can talk about this. How do we identify? By simply looking at this correlogram, how can we identify whether it will be an AR process or it will be an MA process, or how many AR terms are needed, how many MA terms are needed? How do we identify that?
पोळी पण खाल्ली मी आता.
Someone noise is there in the background now. Okay,
they are talking someone.
Okay, so then I have for white noise process, if you look at the correlogram, the spikes, that is this graphical illustration. This graphical illustration will be like this. There will be no significant spike in ACF. There will be no significant spike in PACF in this graph. That is, the band will be something like this. It will be this. There is a spike, but it is within the band, meaning that the coefficient is statistically 0. For ACF and PACF, that is for white noise, it will be generally the ACF coefficient and PACF coefficient at all lags will be equal to 0 for white noise, and there will be no significant spikes either for PACF or ACF. For non-stationary variable, you will see spikes dampen out very slowly. ACF spikes dampen out very slowly, while as for PACF, spikes cut off at certain lag. The spikes for non-stationary variable will cut off at certain lag. You can look at the spike partial autocorrelation coefficient is cutting off at lag 1, and below that there are no significant spikes, right? That's what it tells us. So that means that this variable, particular variable, this which I am talking about here, it is a non-stationary variable. So then I have ARP process, right? If it is AR process of order P, then what will you see? ACF will dampen out, and there will be spikes cut off at lag P. There will be spikes cutting off at lag P. That is, PACF spikes will be cutting off at lag P if it is an AR process. Similarly, if it is an MA process, that is only MA terms are needed. Q number of MA terms are needed. Then you will see spikes cut off at lag Q. ACF spikes will cut off at lag Q, and PACF spikes will damp out slowly. They will damp out slowly. If it is a mixture of AR and MA terms, if a model is ARIMA of order P and Q, that is both AR terms and MA terms are required, then you will find that autocorrelation coefficient spikes are damping out. Similarly, PACF partial autocorrelation coefficient spikes are also damping out slowly. That's what you will. So if both partial autocorrelation coefficient and autocorrelation coefficient spikes are damping out slowly, then as a rule of thumb, you should remember that both AR and MA terms are needed in your model. If you find that there is for ACF there is a spike cutoff at lag Q, and PSF are tapping out slowly, then you should say that, okay, only MA terms are needed. Similarly, for ARP process, follow this rule. This is just a rule of thumb to simplify the reading of correlogram, or that diagram which I have discussed in the previous slide, right? Okay, so I actually thought of doing it in reviews, but as Dr. Balaji highlighted that we cannot share the software because of copyright issues. We thought, okay, we will not do any hands-on exercise. Otherwise, it would have been quite interesting to go through different hands-on exercises. But anyway, so I will stop here. I am quite thankful to you all for your patience and and participation as well. You've been a great audience. I really enjoyed this session, and I hope ditto that you also enjoyed the session and learned to a larger extent. Okay, thank you so much. It was great knowing you all, and thank you, Dr. Balaji, for giving me an opportunity to interact with all these colleagues from different colleges and universities. Thank you so much. Okay, I look forward to see you sometime in future.
It's our pleasure, Sardash, to have you in this thing. If somebody have any questions, I can answer you regarding this thing, because resources already took more than 2 hours, so I just want to disturb them. So I'm here to answer your questions. So officially we can close the session. I can wait for 10 minutes or 20 minutes. If you have any questions, I can answer you. Right, Induja?
Sir, just I would like to thank you, sir, for the way you have explained the concept. It was really interesting. Number one. Number two, so now Balaji, sir, I will ask you a question later on because its time is up. So all would be waiting for this.
The platform
but
is
it was
open.
really good. It is
Yes,
really
those,
good, sir.
yeah.
Enjoyed
Those
it.
who want to ask
Thank you.
question, you can ask. Otherwise, somebody wants to leave, they can leave. It's up to you. Okay, because somebody is asking the questions to him, but we are already occupied his time more than what is supposed to be. So I can help you if you have any questions. Otherwise, you can post in the group. I can help. Induja?
Can you suggest any good book for this time series models?
Induja?
Yes, I would like to take this opportunity to thank our speaker today, Dr. Sartaj Rasool sir, for this wonderfully insightful and interactive session. The seminar had pivotal points that would not only help us in understanding the economy better, but has also given us newer avenues that we could explore. With that, we will be concluding the session.
Thank you so much.
Thank you, Sardash. Thanks a lot for your time.
Thank you so much, Dr. Balaji. Someone was asking you that that share the book they can.
Yeah. Actually, we several times we told them it will be shared once the things are getting from the university. But these people keep on asking. I will take care of it. No problem.
So she was asking for the book. If you can suggest any good book to read all those things.
Ma'am, no, they're asking some PPT, it seems. PPT and recorded videos.
That is okay. But any study material, books.
Well, I think they're asking for books.
Yes.
So
good reference books.
Generally, what I would recommend is, for basic understanding, there is a book which is very commonly followed in India is Gujarati. Basic Econometrics by Gujarati. That's one. If you want to have a little, kind of foreign taste in econometrics, then go for this Woolridge. Okay, book by Woolridge. That's also quite good for basic econometrics. However, specifically for time series econometrics, we have a book by Walter Enders. I think Dr. Balaji might have already told you about that book. It's quite interesting book, and we all have followed that book during our PhD days. I still remember. So that's quite interesting book, Time Series Econometrics by Walter Enders. And there is also another book which mostly deals with financial time series data, Chris Books, right? Chris Brooks. So you can follow that book as well, which is mainly focusing on time series and has much detailed information about time series forecasting and time series modeling. Okay, so you can follow that, and I think that should be sufficient enough for you to help you to understand basic things.
Yeah.
Thank you.
Thank you.
Thank you so much. I wish you all a safe and healthy life ahead. Bye-bye.
Yeah. Bye, Sardash. See you then. Keep in touch.
Thank you, sir.
Yeah. Bye, Sardash. See you then. Take care. Yeah, actually, somebody post some questions in the. Yeah, you can carry on, Sardash. I will take care of it. Yeah, somebody asked whether taking the log values will make the time series data become stationary. Actually, the answer is no. Why? Because log is nothing but the simple transformation of the data with a common base. So even though if you take log, the numbers may be coming to small numbers. For example, instead of being in lakhs and lakhs, it may be in single decimals. So it doesn't mean that the property of the data won't change. So taking log may not make the non-stationary data into stationary. Is it clear? Any more questions?
Sir, one more question. Can you please throw some light on the second order that?
Yeah, generally, yes, I have some little, what to say, the opposite view from Dr. Sardar's thing. Generally, most of the times this data never permit to go for a secondary data. If you took the, why? Because tomorrow Raja sir will going to cover about taking the problem of differences. If you take the difference, what happens is generally you are going to lose the information. For example,
Sir, one more request. Can you please bit slow down your pace?
yeah, okay,
Because
fine.
of the next accent, I'm not able to.
Yeah, fine. Generally, as Sardaj rightly pointed out, you can't, there is no need for you to go to secondary data, second difference. Generally, none of the data will become stationary in the second difference. Why? Because it happens only to the data which you have in disconnections. Otherwise, out of 100 cases, 99.99 cases, the first difference will become the stationary. Okay. So there is no any proper example for second difference. Sometimes it may happen in the population data where you don't have a continuous data. You will cook the data on your own, right? Between the points. So in that case only you are end up with second difference stationary. But out of 100 cases, 99 cases you will get in the first difference itself. Yeah, actually, the general issue is if people wants to apply certain techniques, if they found that there is this data is non-stationary, they will make it stationary. Even that is not a good practice. That is what a model called co-integration is coming to limelight. Tomorrow, Raja is going to discuss those things, right? So what I'm trying to say is that in most of the cases, you never end up with going for a second difference. Okay.
Okay, sir.
Yeah.
Hello,
Any
sir.
more questions? Yes.
Sir, in the previous session, Sardar sir in his discussions said that while predicting the stock price, there might be internal factors as well as external factors, and the internal factors are basically useful when we are going for ARMA structure, isn't
Okay.
that?
No, actually,
So if
yeah, let me tell you the basic easy way of understanding ARMA models, whatever it may be. See, suppose I'll tell you there is a variable called Y. Otherwise, I can tell you with a small example, demand. Okay, what determines demand?
sorry,
I'm
sir.
just asking you a question. What determines your demand? What influences your demand?
Demand.
Yes,
Oh,
demand.
my demand. The
Any demand.
income.
Then
My lifestyle may make my demand influence.
Yes, price.
Price.
Then it's very difficult, right? There may be some thousand number of variables. Okay, we don't know what type of things at all. So it is, if it is the case, if you want to predict something, if you want to go for a better model, even a best model, you have to include all the variables which influence that particular variable. For example, if demand is influenced by say some 100 variables, you have to include every variables, then only you can call it as a good prediction. Okay. But practically it is not possible. So instead, what you can do is you have a demand variable like yesterday. Okay. So what you can say is my today's demand is simply based on my past period demand. Okay. The past period demand is influenced by all the variables which influence the demand. So it is the case of univariate models. So that is what, if you are not very clear about what are the variables influencing your current variable, but you can think about modeling that variable with based on the past information of its own, which means that the past informations incorporate all the informations of the variable which influence that variable. Or you will understand what I'm trying to say.
Sir, I got that point. Sir, besides taking the previous values of a particular variable, can't we merge the other variables too in the same model so that
Yes.
it can?
Yes, it's become ARIMA X model. It's not, instead of ARMA model, it's become ARI XMA model. There is another version of ARIMA model, modified version, where you can include the other independent variables also forecasting. Then instead of it's become ARMA model or ARIMA model, it become ARIXMA model, ARIXMA model.
Okay, sir. Sir, X stands for?
X stands for independent variable. X is nothing but the independent variable what we use in the modeling. Y is a dependent variable, X is the independent variable.
Okay, sir, got sir.
Any more questions?
No, sir. Thank you, sir.
So are we going to have this session on when our data is not stationary?
Sorry, sir, come again. I'm not getting it.
Are we going to get a session on this when our data is not?
Yes, sir. See, sir, the entire time series analysis is based on a property, sir. We have a data. Okay, I'll just make it in just 2 minutes. The history of time series. Actually, it is supposed to be start the very beginning. Uh, the entire time series analysis start with the content called spurious regression. Initially, before the modern methods are developed, what people used to do is they pick some two variables, x and y. They simply run the regression and make the claim that x causing y or y causing x. Once the literature develops, theory develops, people come with the idea stating that you can't simply pick two variables and you are not supposed to do any analysis, because if you are doing so, there is a possibility of committing an error called spurious regression. Spurious regression means nonsense regression. I'll tell you a small example. I can say India's GDP, it depends upon number of the percentage of your attendance. Even we pick the data and regress with GDP, I can get a positive result, high positive results. But technically, there is no association between these two variables, right? So if that is the case, when the literature emerges, people say that the data what you are using is supposed to satisfy a condition called as stationary. That is what we're discussing. Unless until both of the data is not satisfying the condition of stationary, you are not supposed to use it in the model. It's a very beginning stage. So what is the process? What is the next stage? So what people used to do is, if the data is not stationary, just make it stationary. How to make it stationary? Just take the first difference and estimate the model. That is what the theory emerges. But in the year 1980s, people like Angel Granger and a few more people come with a different idea, stating that it is not the right way to make the non-stationary data into stationary, because in the short run, the non-stationary data may not have any relationship, but in the long run, these two variables may share the common trend, which is called as co-integrated. So the entire analysis is distributed in these two components. Whether the data is stationary, then you can apply a set of techniques like ARIMA model, VAR model, impulse response, Archie-Karsh models. The basic conditions for applying these techniques is the data must be stationary. What is the other method? The other method is something, if the data is not stationary, then what is the process? Instead of taking the, instead of making the non-stationary data into stationary, just apply a technique called as co-integration. In co-integration, we have different set of co-integration, bivariate models, and then multivariate models. Okay, that is what Raja sir is going to cover tomorrow. There is one set of model which is called as ARDL. Suppose you have a combination of variables where a set of variables stationary, a set of variables non-stationary. Then what you can do? You can't apply either co-integration or the other stationary models. In that case, you are supposed to apply a model called as ARDL, autoregressive distributed and lag models, proposed by Perron and Shin. Morning I discussed about this tool, for which a software is developed by these people like Microfed. Microfed is the software which is developed to solve the problem of ARDL only, right? Sir, Rahul sir?
Yes, sir. Yes,
Are
sir.
you able to understand the logic?
Yes.
This is how econometrics emerges. This is the history. This is the tree you have to understand before applying any techniques.
Okay. Thank you,
Any
sir.
questions? Yeah, thank you. Any more questions? See, it's too early to ask about mode of exams. See, I want to tell you that don't ask resource persons about books. Okay, you ask, make use of them with some interesting questions. I already told you several times, the videos is not recorded by me. It is recorded by our university. They will give the comprehensive video only. Everything is over. Okay, even you ask me, I can't share it now. So every day there are people who keep on asking the same thing. I keep on posting the same thing in the group itself. It seems that nobody is reading whatever we share in the group. Just keep on watching it. Any more questions?
So like the PPTs, the resource persons are teaching through. So can we get those PPTs even after, like you're saying, after the this workshop is over? So
Yes, ma'am. No. I already asked them to share it. We can't insist them, right? I already put a request to them to share the PPTs. Once I received, I will share it. Don't worry, because I'm not going to keep it with me, right?
No, yes, sir. Yes. Okay. Thank you, sir.
The resources for you people only. Yes. Any more questions? My kind request is that please joining on time. Yeah, I do understand there is quite difficulties over there, but once it is not good to ask resource person to wait. Okay, it's a little odd. One more thing is, if somebody is not really attending it, just at least switch off your mics. You may hear that some child is crying, behind that some lorry is going, so it is not a good attitude, I feel. Okay, any questions? If you don't have any questions, we can officially close today.
No question. Thank you.
Yeah, please.
Yes, sir.
Yes, thank you all.
Apology, sir.
Yeah, thank you. Have a nice day.